All right, great. So welcome everyone. Thanks a lot for joining this workshop. So the plan of this workshop is to take you from this situation over here, where you have your code that is without a doubt the worst that has ever run, but does run, and make it the best that has ever run. So this workshop is full of these memes. I love them. What's happening? We have something that is divided into 6 blocks. So 2 days, 6-block workshop. I have been developing this bad boy for a lot of time now, combining a lot of resources. So I really hope it will be useful for you. It has definitely been useful for me in my, let's say, science career. Some quick disclaimers. You have to understand that you will not walk out of this course being a master of coding. You will have to revisit things and work on things. It's not instantaneous. You will have to iterate, okay? And of course, while a lot of the stuff I will present are indeed general, let's say, rules or general guidance, some will be personal opinions as well. So take everything with your own judgment and act accordingly. The blocks are first version control, then how to write clear code that people can actually understand, and then how to incorporate software developing paradigms into your own code and developing your own code base. Tomorrow we start on collaborating aspects, how you can collaborate and publish code online and work with other people in the same code base, how to document code, and how to make your scientific projects reproducible. So that's the plan. Hello everyone, so this is George from the future. I'm recording these videos after the live recording of the workshop. And I will be showing these extra, let's say, recordings throughout this video workshop to add some additional information that make more sense for people watching online, or to simply correct things that I learned during the workshop. So the workshop you're seeing is mostly language agnostic, so it gives you principles about general coding. There will be examples and exercises, a lot of exercises in Julia and Python. One important change that I want to highlight is that this workshop has 6 blocks. When we first did it, we showcased these 6 blocks over the course of 2 days. Now it is clear to me that you need much more time, and what I recommend is that the students and the tutors take each individual block and go through it fully until the students have done all the exercises in the block, also for their own code. So what we recommend now is to spend 1 day in each block and even 2 days if necessary. Another thing that is very important is that the major components of this workshop are the exercises, and the exercises need tutors to help the students and guide the students. You can take this workshop solo if you're watching online, but keep in mind that during the exercises it will be helpful for you to have someone to help you. So maybe you can go to forums online and ask for help there. The third thing is that you should approach this workshop with your own code base. This means bring your own science code from your latest science project and take, let's say, the code that creates 2 or 3 plots from your recent paper or your latest project. We will be working on this code and trying to transform it to something really, really useful. So every block has exercises that are about your own code. Bring your own code. The workshop materials are available online. I strongly recommend to download the new slides. The slides that you will be seeing during the live recording have been improved. Now there are better versions of the slides online that make more sense. Yeah, that's it from me. Good luck and enjoy the rest of the recording. Okay, let's establish the mindset we want to be approaching code. What is the purpose of code? Well, technically you would think codes are instructions for a computer to do some specific things. However, another way to look at it is that code is a means to solve a problem. And here is a very nice quote. Programs are meant to be read by humans and only incidentally for computers to execute them. This is important to keep in mind because it means that code is written and read by humans. It is just another form of technical writing. Similar to a paper. So think your code as a paper. You expose information to other people. So it must have crystal clear communication of the problem solving. My opinion of what is good scientific code: it is something that is clear, easy to understand, well documented, reproducible, testable, reliable, reusable, extendable, and generic. Now this sounds like a lot of properties for code to have, but I promise you in this workshop, not only you will learn how to achieve all these things, but you will also learn that they are not costly. You don't have to devote months to make your code base like that. If you know how to do it, you do it while you do it. At least that's the promise, right? One more thing I will address before we go into the workshop, and I'm sure you know this is coming. You have to understand that modern tools over time typically become better for some tasks. So think about the tools you are using right now. Think about what you want to achieve with these tools, and think about maybe there are more modern tools or better tools that do the things you want to achieve better. So if you're using X programming language, but your tool is, or your goal is, oh, I want to do a lot of science, which is plotting, interactiveness, prototyping, and stuff like that, maybe an old statically compiled language like C is not the best tool for this job. So think about this carefully and make decisions. And of course, you know that my recommendation is to use Julia, which is the tool that achieves everything, in my opinion. And you would never need a second tool, but this is clearly my opinion. But the first part is something important. Think about this. You might be using the wrong tool for the job. All right, so we start with version control. If you already know version control, please don't leave the room. Just help the others solve the exercises, okay? You can make yourselves useful. What is the dumb and the smart way for code history? Well, the dumb way to store a daily backup of your file or whatever copy with a different name. So we've all been here. We have paper text, paper final text. Oh no, paper really final text, paper version 1 text, paper version 3 with Richard comments text. So this is the dump system to version control, which means to keep history of your code. Because it is practically impossible to use in collaboration, it is super duper error prone, and it has a large overhead. You just store a lot of files. The smart way is something that are called version control systems. And they have some very nice properties that help us. They track changes in every file without renaming files. They allow reverting to previous versions of files or the entire project without losing the current version of the project. They allow several different instances of the code base to coexist in parallel. They facilitate collaborative editing of files by different parties safely. And they allow tracking of who made changes to the project, when, and hence accessing the chain of blame. So, because in this course you will be modifying your code base a lot, it's best to start by learning the system that makes code modification safe and retraceable. And that's exactly what block 1 is. So block 1 is about Git. Git is a command line tool that is the most used version control system, to my knowledge. And it is super efficient because it only stores differences from previous states. It doesn't store each state once every time. So if you imagine the first version of the project had 3 files A, B, C, the second version has a change to file 1 and file 3, but doesn't have a change to file B. So this file B is kind of shadowed or linked to its previous version without being copied over. And this order continues all the way to the end. At each time, you just store the differences necessary to bring the original version of the file all the way to the last version, just the differences. So as I said, this is a command line tool, which means you access it from your console. If you have a folder, you can immediately make it a Git repository, so establish Git as a control system by running the command git init, nothing else. And then everything will be retraceable and everything can be recovered, even if it is deleted, provided, of course, that you use Git properly. So this is my take on Git, that Git is the closest thing to time travel humanity has. I really like it. So how does this work? Does it work? Well, your files have 3 possible states to be in. They can be modified, staged, or committed. You can think of these stages as the processing line of a factory, for example. The modified means that you have made some changes into the files, but nothing else. The staged version means that you have indicated to Git that these files are ready to go into the code history. And the last stage, which is the committed stage, means that you have stored the files in the code history with all the changes, and now they are there, and you can access them again in the future. So that's it. That's the 3 stages. That's a useful way to think of them. Factory processing line. As I said, at any point, ask if something is not clear, right? I will be going through without stopping unless someone actually stops me. All right. So how do we do these things? How do we access these states? Well, you first start normally. After you have initialized your Git repository, you just go to your ID, which is Integrated Development Environment, your editor, and you just edit your files. That's it. This automatically makes the files be in the modified state. Then you have the command that is called git status. That shows you the status of the current Git state, or which files are modified, for example. And then you add your files to the staged state with the command git add. You can add specific files, you can add specific files that all have the same ending, or you can just add everything. So you just use git add to add the states to add files to the staged version. And then to move the files from the staged version to the committed state, you simply say git commit. This command by itself will open an editor where you type a commit message. There are other varieties you can do with git commit. But let's talk about this thing, because this is when you store things in your history, right? So if you think about it, this is actually really important. After git commit, you get an editor where you write a description of a commit. And this line is called the commit message, and if you don't want to open an editor, you can use the command -m and then quotes and actually write a message. Now this is really, really important. This is the most important part of this commit. You really should try to get this right. This really allows you to scan your history with your eyes and see where you should go without further analysis. So it's useful to be clear about the commit messages and not just say some commit or add data or add files, okay? Try to make them short and to the point, and try to avoid useless information like commit author, date that you did the commit, branch that you did the commit. Because all of these things are found immediately with the formal tools of Git. You don't have to repeat them. If you want more description besides this one sentence that is the git commit message, then you can leave an empty line after the commit message and start writing many things, like full paragraphs, like write a novel, we don't care. Just a quick notice here, in other Git environments like GUIs or GitHub or whatever, there is actually a separate text box for the message and a separate for the description of the Git commit. I was a bit confused by that, so I'm letting you know. Don't be confused when you see an actual editor, Git editor. And another important point, commit regularly. So don't just work for months on your project and then at some point you're like, oh, maybe I should commit, right? So a rule of thumb is any change that you can summarize in a sentence should be a commit. If you need several changes to summarize the change in your code, you probably should commit more often. So here's a nice meme that highlights this. Me playing video games, save every 5 minutes, me writing code, git commit, some changes, 600 lines of code change. So try not to do this, okay? All right. One more slide and then we go into the first exercise of the course. So, how fast did I go? Okay. Sometimes you commit something, but then you immediately notice, let's say, a typo that you did, or maybe a simple one-line change that you believe should go into the same commit with the same description. This is easy. To immediately add these changes to an existing commit, you use the git amend command. And now we go into the juice. The main strength of doing all this work, of committing files regularly and thinking about your commit messages and wasting your time getting the good commit message, is because you can reset to previous stages of your history. So this very, very amazing command called git reset, and then you give it a commit ID. You will see what the commits ID are once you start the exercises, don't worry. This allows you to bring your code base back into the selected commit. So every time you commit, there is a unique identifier that is associated with this commit, and you see this when you commit, and you can just copy this and paste it here, and then you go back in time. And there are two noteworthy options. There are many, many options, but there are two noteworthy ones. One is to add the flag soft. What this does is it reverts the status of the Git, let's say the Git history, into the state that you want, the commit you want, but all the changes that you have done are now unstaged changes. They are just, it's like you modified files, but you didn't commit them. So do you understand what's happening? Is it clear for everyone what I said? The state of the Git history goes back in time, and every change required to come to present is an unstayed change, so they are modified files. Clear for everyone. All right. There is the other version, which is the hard reset, which literally deletes every change and just brings you back to past. So the files you have on your computer becomes the files you had 5 months ago when you did the commit. All right. And there is one more option that is useful, and it's called git blame. So you can, with git blame and choosing a specific file, this shows you a history of who and when edited this file. And you might think that this is used for bad people that like to blame people because they're bad. That's actually not true. Well, it is true for some people like me. But in general, this is an extremely useful tool. Why? Because the author of the change is the most likely person to know why the change was done. At least if it was done recently enough. If it was done a year ago, good luck. All right. I love this. That's a nice meme for the git reset. Okay. First exercise. What's the time? Woo, perfect. First exercise is to start doing some commits and start resetting to previous commits. So if git is not installed, do it now. Create a local empty folder. Initialize git in this folder. To commit things, you have to configure your username and email. It doesn't have to be your true username and email, but I strongly recommend that it is. And in there, in this empty folder, just create a dummy test file and write something in the first line. Use git status to see that indeed the file pops up as modified and everything is nice. And then stage and later commit the file with an appropriate commit message. You can decide that. After that, edit again the test file and add a second line of text. Doesn't matter what line it is. Commit the change. And now we start working on how reset works. Because suddenly you realize that your change was very, very bad, so you want to go back in time. So first do a soft reset so that the git history goes back in time, but your file, if you open it in your editor, is exactly the same. It has not changed. But then, and then you can commit again by doing some small change, but then reset again and do a hard reset. And then you lost everything in the second line of this text file when you open it, and that's okay, that's normal. So I leave the slides there. Go through the slides I uploaded if you need to see the commands again if you're not sure. I'm moving on, okay? All right. As I said, everything stays in the git history even if it is deleted. This means if you have added into your git history a large file, you're kind of fucked. This file will exist forever. So there is this very nice and special file called gitignore, whose contents I show you, for example, on the right side. So it's called .gitignore. Let me clarify this. It is a special file in your Git repository called .gitignore. Okay, it's not just gitignore, it's .gitignore. It's a text document. And there you may add files, directories, or file endings that you do not want Git to track. So typically there you would add all of your binary data, your plots, things that are large in size and you don't want to track. They don't produce things, they are just things that have been produced. So keep this in mind. This is really important for real world projects where you actually have large files and it's not just a text document saying, I don't know, some commit or whatever. Okay, so it's .gitignore this file. Top level on the repository. You have to create this for your own code base, I mean. All right, now we go into this really useful part of Git, which is branches. Well, okay, first of all, Git has the concept of tags that allow you to mark a specific commit with a special name so that you don't have to find these 16 random characters weird thingy anymore. You can just use a human readable name. And you can revert or reset to tags just as well to any other commit. For example, you may have a tag submitted for the version of the code that you submitted for publication with your paper. All right, now branches is one of the most useful properties of Git besides the time travel stuff. And what are branches? So first of all, you can make branches with the extremely simple command git branch and then the name of the new branch. So branches are parallel instances of your code base. They are different and independent of each other that have the shared history up to the point of branching. So really think of them like a tree, really. And they can be developed completely independently. And you can jump from one branch to another at any point by using the command git checkout and then the name of the branch. And typically, the first branch or the main branch is called main, and all other development branches are merged into main. So now I just said this word, merged. This is a keyword. A branch can be merged into another branch, which simply adds the changes that are being tracked by one branch into the other branch. So this is actually how you do changes in your code. That's the real way you do this. You do the staging and committing and all this business, but you don't do it in the main version of your code base. You do it in alternate realities of your code base, just to be on the safe side, and for many other reasons that we will discuss tomorrow. Quick note, if you have done a change in the same file and in the same line in two different branches, and you try to merge these branches, Git will show something called a merge conflict. It doesn't know how to add the changes because they are conflicting changes. And now you, the human, must manually decide which change survives and how, either in a dedicated editor that Git or some Git GUIs provide, or by manually adding more commits to one of the two branches to resolve this conflict. There are different ways, so to speak, but be aware of this. Okay, so that's a nice meme that highlights the merge conflict. All right, now there are different ways to merge. Let's say there are typically three ways, or not typically, there are three ways. The first way is the merge commit. Actually, let's just highlight these three ways. Lucas, would you please do the honors? So here comes the Git, the big reveal. I don't know how to use Git. Seriously, I don't know how to use the command line. I use a completely different tool that I will show in a moment. So now we need the help of the experts to actually do this thing. So now we will highlight how the different ways to merge work. Yeah. So the first way is the merge commit, where you have two branches and you make one branch go into the other with one additional commit that says, oh, this is the merging of the branches. So this commit is, let's say, more like a dummy commit that shows the branches being merged.
Like maybe a short introduction for that tool. That's a nice showcase that highlights how a dummy repository would look like. Because as you've already seen in the first exercise, one of the problems when trying to teach people Git is that you actually need like a software, it's some shape, and you need changes to have different versions. And if you try to manufacture them, things always get a bit weird because you tell them, yeah, then type your name and then make a typo and then add an S and add another line or whatever. So half of the exercise, you just end up manufacturing arbitrary changes to a code base in order to be able to show differences or to show commits. And this tool tries to help that because it is more about the shape of the repository, because what I can do here is I can simply do a commit. So I haven't changed any file because it doesn't know about files. I haven't added anything. I didn't have to write a commit message that just said changes. I can just repeat those things and just do commits. But what this tool does and what it does nicely is it shows how different commits relate to each other. So one thing that you can see is that a commit always points to its parent. So the latest one where our master branch currently is, the green dot, points to its parent. And every time I create a new commit, it will point back in history because that's what its reference is like. And what we can also do is we can create a new branch and check it out, where we, for example, want to do our own features. Like George already said, that's the way how to use Git. So you barely work in the master branch, but if you want to change things, you will do it in the feature branch, which has two advantages. One, if you're collaborating with other people at some point, you want to have this one version, like the master or the main branch, that is still working. And you only have update that if a new feature is fully developed and ready to be merged in there. But also for your day-to-day work, if you say, like, I don't care about collaborating with other people, I'm a scientist, I do my own stuff in my own office quietly, you probably were in the situation where you wanted to change something, and so you started to develop your program to a point where it didn't really work anymore, and then your supervisor knocks at the door and says, hey, I need that plot you did yesterday. But then you're in this half-ready shape where your program actually doesn't do anything, not the new feature, but also not the one that you have done before. And if you've started your development in what is called a feature branch, you could then always check out the master branch and repeat the plot from yesterday, and afterwards continue to developing things. And so in the best case, you've checked out your new branch, you did some commits there, and now the absolutely easiest way that could happen, that's this non-collaborating work where you're sitting just in your office, but you've reached a point where the feature branch is ready. You can go back into the master branch, maybe without the typo, probably do it. And you can see that now the master branch again is the green dot, the head, which is the currently checked out branch, and you could just merge whatever in feature is. And now in this very straightforward way, it will simply tell Git, okay, I'm done with all my development. Just regard that as the new master now, that commit. And I would argue that in 90% of the time for you, that's probably sufficient, and that's how your development will work. But what can happen as soon as we are in the real world is that other people have also done things in the master branch. So that has also developed. And then there is different ways how to bring those different branches together. And the straightforward way that George already mentioned is just a so-called plain merge. So you say from the master branch on, I want to merge whatever has happened in feature. And what that will do is it will create a special type of commits. So before, you've seen that every commit has this one error or one connection to its parent. And this commit actually points to two other commits, because it will say, okay, now I reference two different states or two different trees of our repository to include both changes at that point. But you can also see that this has the problem, if you want to time travel or go back in time, this will be already a rather confusing time travel movie, because it's not clear which branch to follow. So it's hard to tell in which order those changes occurred, if they even thought about it, which one came first. So if there are any problems and the program doesn't work as intended anymore, it's hard to tell whose fault it was, so to say. So there's different ways to handle that. One way, so if we haven't done that yet, is to do a so-called rebase. So you're in your feature branch, you realize the master branch has evolved in time. So you say, okay, I was too late, it took me too long to finish my feature, the main project evolved, so I will acknowledge that and I will incorporate their changes into my feature branch first. And that can be done by using what is called a rebase. So the base of a branch is already the one commit where you left the master branch. So here it would be this commit with the ID 663, whatever. So there where we have the two ways separating each other. And what you can tell in your feature branch is to say, I want to rebase it. I don't want that commit to be the base anymore, but I want the master branch to be the new base. And this tool very nicely illustrates what's happening. It will then rewind all the commits that you've did in your branch, keep it like at the side of your project, check out the master branch, and just try to reapply all your changes. And the nice thing about that is that if you only follow the one existing line of development that you can see now, is that we are back in the stage of before. So now you could simply check out master again, merge the feature branch, and have this linear, clear history. Also with the advantage that it's clear what happened first. So if people look at that, they will really see, okay, there was this one development that happened in master branch, and then there's your feature that came to it. And there is a third option, which unfortunately is not so easily depicted in that tool, because one of the disadvantages here is because it's so agnostic of the files that are actually in there, it cannot really tell if conflicts would occur or if things could be squashed or merged. But the third option that often is used is a so-called squashed commit, which is actually related to this rebasing approach. It will just take all the changes that happened in your branch, squash them together in one commit, and then only apply that to the master branch. So it ends up in the same situation, so to say. You have this clear linear history, and there's just massive flame wars in the Git community which to prefer. So some people say the squash commit is the better way because it's cleaner, it's easier, you only have this one commit, it works or not, and all the changes in a branch should be related anyhow. And there's other people who say, but I want my branch and all the individual commits in there to be verbosely telling how the development evolved. So if you have different stages, like I refactored the code first, then I added another feature, then I wrote documentation, I want people in the review to be able to follow that. So there's different approaches how to handle that. But in general, when you do your development, you should do that on a separate branch. Then there's different ways how to get that back in master.
So for this course, just simply imagine all the purple dots would be dot. That's it, really. That's the main difference. All the purple dots would magically become one dot instead of how many they are. It doesn't matter how many they were. It could be 500. They would still become one. Yeah, so as Lucas said, two different approaches. So for large collaborative projects, the developers would typically suggest squashing. For example, the maintainers of the Julia data frames library recommend to always squash, because in these cases, the history of the final product does not matter, but mostly the product itself. And it's easier to cherry pick changes if you have several release versions. So if you have a long-term support version, like you only support version 1 of your language, but you also have another version of your code base that supports some future version. But this doesn't matter too much for us. Rebasing is actually really useful in solo projects or projects with small teams, so you can really justify better the choices or better blame people or see the history better. And as Lucas said, I will repeat it because it's very, very important. Best practice, and everyone agrees on this, there is no flame war here. Best practice is to keep your branches small and focused. Seriously, small and focused. So if you are on your branch and you're noticing, oh, I could do this quick change like in 10 minutes, this extra feature. No, you will not do it in 10 minutes. You know this, so better accept it and keep the branches focused. All right, second exercise. Git merges and maybe Git conflicts. We'll see. I say here total exercise time 30 minutes. That's kind of crazy, but okay, let's see. So you're in your main branch now. We continue from the previous exercise. You're in your main branch. Create a second branch called bud. Name this branch bud and switch to this branch. Add some kind of second line of text to your dummy text file and commit this line. And then check out back to main branch. So you will notice that this second line does not exist anymore. There, create a thread. Actually, there is no reason for me to read this. Just read it and do the exercise, okay? And if you have questions, just ask me. Why am I reading this? It's over there. Go, do it. Go, branches. Very important to learn to work with branches. Seriously, very important. Let's go. So the reason I said I don't know Git is because I have never actually used it, because I use this tool over here called Git Kraken, which I strongly advise everyone to use as well, personal opinion, and I'm not endorsed by it or anything. It's just a spectacular Git graphical user interface. It looks like I showed you on the slides, or like this. This is my repository for the programming workshop. It has the trees or the history you saw when Lucas was presenting over here. You can make branches by clicking the branch button. If you're dumb like me and you don't want to dummy branchy, you can make a branch over here. You can go into your whatever, let's say log1 git, make a new file, test, and then you go here and test will be visible. You can state the file, you can write the commit message, commit the testy boy, click commit, then you can go back to main, click, where is it? Reset dummy to this commit. Okay, I'm not going to do this now. I don't want to risk losing anything. It also has its own internal editor to resolve changes, so you don't have to go and see all these weird arrows. You just see two versions of the file, one with orange highlighting and one with some other highlighting, and you can click and choose which version you want or which change you want. You can click both of them at the same time, and it automatically makes them both go there. Fantastic stuff. It's absolutely amazing. I strongly recommend using this tool. So yeah, that's how I use Git. And this is also where I do my merges, my branches, my resetting, everything there. Also searching commits. It has a nice search bar somewhere at the top that I don't see now. Many other graphical user interfaces exist for Git, of course. This is just the one I prefer. VS Code, the editor I use, also has an integrated Git support. And this is fully free, but its timeline view isn't as nice. Just a quick note, because I'm advertising this. If you have remote repositories that are also private, then this tool is not free. You need a license, at least according to their website. Okay, that's it. Now we are at the end of the first block, so you can use the remaining, let's say, 40 minutes to exercise. If you haven't solved the exercises, feel free to continue. This is now the exercise where you apply this newfound knowledge into your own code base, the one you are supposed to bring here and work on it on every block. Initialize a Git repository for your own code base. Make sure the default branch name is main instead of master, because master is not a politically correct name, apparently. You can use this command to rename branches. Git branch, capital M, old name, new name. So rename, be sure that main is your main branch. Think of the gitignore file and create this file. Remember, it's a file called .gitignore. It's just a text file. There you put files that should not be tracked, like plots, data files, or entire directories, like the plots directory. Commit the initial version, so add and commit the initial version of your code, and then also create a tag with the command git tag, name of the tag. Here are some suggestions. You can name it same, or never look back, or please help me. I don't know. And from now on, for the remaining of this workshop, every exercise that is about your own code base will be done by making a branch, developing the exercise solution, and then boom, merging the branch back into main. Okay? So that's the end of the first block. All right, this section is about clear code, which means writing code that is easy to understand by other humans, preferably. This is another nice meme that I love that describes how non-clear code might look like. I love this stuff. Okay, why? Why should you do that? Well, the first reason is that it's easier to understand. Code that is clear is easier to understand. Sounds obvious because it is. It makes bugs harder to hide or easier to find. And it is important for your collaborators. You know, you might say, dude, I work by myself. I don't need other humans. Well, the problem is your future self is by far your most frequent collaborator. So pay respect to your own self and actually write some readable code. It's easier to extend. It looks professional, which means if someone reads code that is easy to understand, they are much more motivated to use that code instead of starting from scratch. And it doesn't conflict with performance, something that is a common misconception. People think, oh, if I write code that is clear, it won't be fast. That is absolutely not true. It's easier to reproduce and retrace. Nice. That's the end. That's the reason. Many reasons. Okay, we start immediately with perhaps the most important part about clear code, that is naming. How you name things is super important. I have two versions of a function that do some operations, and what is clear is that the code is not only identical in these two cases, but the operations are understandable, at least for me that I read this language every day. It is clear that here the function push is called, it is clear that here the status field of this object is called. These things are clear. What is spectacularly more clear in the second version is what the code actually aims to do. It gives you the flagged cells of a game board. How would you imagine that this is what a code that says get them from B, go over the X in the B, and if X is 4, put the X in the list and return the list? It is impossible for you to tell a clear story because nothing here conveys a clear purpose. Well, here, every single line conveys a clear purpose. I want to get the flagged cells of the game board. I start with an empty list that I call flagged. I iterate over the cells in the game board, And if the status of the cell is this constant called flagged, then I put this cell in the container, and then I return the container. So the motivation, reasoning, and outcome is much clearer in this version on the right. So naming is crucial to convey the story of what code does. Naming is crucial to convey the story of what code does. All right. Let's talk about brevity. Should you write concise names? No. No, you should not use concise names. Use intention-revealing names and avoid abstract, meaningless, one-character names. Names like data are simply too abstract to be useful. Names like foo and buzz are simply meaningless to convey any purpose. And names like ABC are simply too short to convey any purpose. And keep in mind, people always find concrete examples easier to follow than abstract examples. So, there is always something specific that more likely better suits your case, your use case, than a generic name. Here is an example: birth speed instead of B, days since creation instead of C, etc., etc. And always err on the side of clarity instead of brevity. Now, I have to say, there are of course cases that brevity is the much more sensible choice. Here are two characteristic examples. The first is dummy variables which only have meaning within the code block they are defined. Like the indices I and j here have only meaning in the code block they are defined, and it is much more readable to have this code block that says right index and left index. Okay. Another case where brevity is clearly favored is variables whose name is only meaningful in the caller. What does this mean? Imagine that you write the code for the mean function, mean of x. What x is not meaningful for the mean function, is only for whoever calls the mean function. So I might be a researcher and I have a time series of precipitation, and there x would not be x, would be precipitation. So this is what I mean, but within the source code of the mean function, what x means is nothing, it doesn't mean anything. So there you can use one character name like x. All right, let me give a concrete example of where brevity really should be avoided. Because besides being uninformative, brevity can lead to two similar names that can be confused too easily. Here is a pop quiz. I have three variables on the screen. What do you think these variables represent? These are actual real variable names from actual real code in our field. If you know the answer, don't say, but you can see from the name of these things, it's extremely difficult to tell what they are. So here's the answer of what these things are. RSTT is short wave irradiance, short wave irradiance at the top of the atmosphere. I am already laughing because it is insane to me that someone thought that these four letters convey something so huge. I need an entire sentence to describe this, yet for some reason, four letters are apparently the way to write it. RSUT is short wave irradiance at the top of the atmosphere, outgoing. RSUS means short wave irradiance at the surface, outgoing. So, I'll try to make this as clear as possible. Typing characters isn't a big deal. The finger muscles is the muscles you would probably use the least in your scientific career. So please go take the time and write characters so that variable names are actually understandable. Use long and descriptive names. There is one more reason to do this, and that is it is statistically guaranteed that these three names will be mistyped for one another. Their Levenstein distance, which is a metric on the strings, is only one, which is the minimum possible for words that are different. And in fact, this is the basis of autocorrect algorithms. The way autocorrect algorithms work is they estimate these distances between common words and say, you most likely use that word because it is too similar. So it is statistically certain that these words will be confused. That's one more reason to use long and descriptive names. All right. Okay, so Unicode is something that I really like, but unfortunately I'm sad to drop it. So in case you didn't know, new programming languages allow the usage of Unicode characters within code, properly and formally. Everything that you see over here is totally proper and valid Julia code. Everything works. Actually, it could also be in Python. This is not, Python also allows Unicode. There are some clear advantages in actually using Unicode in your code. It can make mathematical expressions feel natural. It can allow you to exactly write a paper formula in your code, exactly it was in the actual paper. It can allow you to use unique symbols that you use throughout the code base. For example, instead of real, I could use this Unicode symbol for the reals. Or except of outgoing and incoming, I could use up arrow or down arrow. Unfortunately, there are also some very obvious disadvantages in Unicode. It is hard to input in some environments. It is really, you don't even know how to put encode characters. And some terminals cannot display Unicode characters because their default font does not have the Unicode representation for this symbol. It might be unclear what Unicode code to use because there are many Unicode characters that represent an up arrow, and just by looking at it, it's not immediately obvious which up arrow this is. And some Unicode symbols may look very similar. In some fonts, alpha and A are very similar looking characters. And also some Unicode symbols can be confused as operators or misinterpreted as operators. Like this star over here, many people that do not know what this code means might think, hey, is this star an operator, like an exponentiation or whatever? So my advice would be to use Unicode for read-only things, so things that the user will read but not write, like documentation strings, low-level code, comments. But to avoid Unicode for things that the user is actually expected to write, like the names of functions or the names of keywords that the user will actually type, or variables that are expected to be reused in a script that you want to give to your colleague or whatever. So that's the story with Unicode. Ah, nice. This is a nice meme that highlights what happens if your terminal doesn't have Unicode characters. It will just show you squares. So that's one of the bad things about Unicode. Okay. Some things to avoid when choosing names. Avoid misinformation. Don't name something a customer vector if it is not a vector but a dictionary. Don't name something a customer dict if it is a dictionary of employers instead of customers. Avoid constant literals. Don't write 2020 in quotes and just use 2020 in quotes in your script that downloads ERA 5 data from wherever. Define a variable called year and assign the value 2020 to this variable and use the variable year in your script. And in general, assign as many constant values to variable bindings as possible. It makes your code more generic and more extendable. And try to avoid numeric suffixes. Now, like agent 1, agent 2, position 1, position 2. Sometimes it's true that enumeration by the integers is the most fitting thing, but it is most often than not the case that it isn't. The variables will likely have a more meaningful separation for them, like agent junior and agent senior, or position old and position new. And this also more clearly establishes ordering in your variables. Because what is 1 and what is 2 can be arbitrary, but what is old and what is new is not arbitrary. Okay? Another thing to avoid is something that is called Hungarian notation. I do not know why it's called this way, but it is the notation where you encapsulate the type of the variable within the variable. I never ever use this, but there are two reasons that it is especially important to not use this. If the type is obvious from the context, or if your programming language is typed and therefore allows you to annotate the type programmatically, so it is asserted. So here I have a variable that is called birthdays dict, and I hope it is clear that dict is a completely useless addition to this name because it is clear from context that this is a dictionary. Here I have a function called employer birthdays that takes a variable employer vector. Vector is useless here because it is much better encoded as a type annotation. So here I say I just have employers and I want my language to assert that this will be a vector. So the second version is much more readable and I just use the employers throughout my code base. There is one exception that I want to pose to this rule, and that is variables that are Boolean, and there I strongly recommend to use the prefix is or has. For example, here I define a variable has water instead of just water, which checks if this air parcel has water or not. And I define a variable is prime instead of just prime to check if a number, or to encode if a number is a prime number or not. So this is something I strongly recommend. From experience, I found code that does this much more readable for Boolean operations only. For the rest, no. Okay. Another thing that is important is to acknowledge and really follow your language's style guide or the expected style guide. What does this mean? Or another way to say this is the language convention. So as far as we know, in Julia and Python, the following convention is used for naming. Functions and variables are typed in lowercase with underscores when necessary. An example with a long name that has underscores. Types or classes are camel case and without underscores. So camel case is this type of notation where the first letter of each word is capitalized and you glue everything together. Global constants are always all capitals with potential underscores, like these two examples. And here is the difference between the two languages. In Julia, the modules are camel case, while in Python they are lowercase and without underscores. Following the language conventions are super cool because it allows people to read your code faster because they can make assumptions about the role of variables without having to actually confirm that the assumptions are true. If I read the code and I see something in all capitals, I immediately assume this is a global constant that is asserted, and I don't have to double check and really confirm that this is true. The same case goes for camel case where, oh, I know this is a type or a class, and I don't have to search to confirm this. Not following them, on the other hand, can lead to confusion, because if I read the code and I see a variable with a name with all capitals, I would never think that this is a function. But if you wrote a function with all capitals, we have problems. Okay? Clear so far? Please stop me if something is not clear, right? So if I'm going fast, please stop or say or do something, I don't know. All right, that's a very nice meme. No, don't do that. You're not necessary. You can write good code and then move forward. First exercise. So in the repository, I have uploaded a file called badnames.jl. This is a file. Well, actually, I can just show this file. Just download this file. This is a file that has two cases, two functions, let's say, two pieces of code that do something. I named them as badly as I could. Your goal is to first understand what these functions do and then rename as many variables as you see fit into a version that is readable. I'll give you how much time? Let's say 10 minutes, and then I'll present the solution I came up with. So go, download this file, start editing. Both cases, please. Do I have a Python version? Oh, shit. We didn't do a Python version. Don't worry. The next exercise has a Python version. But it doesn't matter that this is Julia. This is not an exercise in the programming language. Just change the names, nothing else, okay? You should not change the code operations. If the code is runnable now, it should be runnable afterwards. Don't change operations, only the names, okay? All right, please raise your hand if you have understood what both cases, both functions do. Raise your hand if you have understood both pieces of code I gave you. Git, not even you? Okay, so okay, one person. When you're reading code, you want to be able to understand 20 lines of code in 20 seconds, not in 10 minutes. Here you had 10 minutes and still you were not able to do it. The purpose of this exercise was mainly to really show you as explicitly as possible that if code is badly named, you are at the hands of the gods, okay? It's really difficult. Of course, and if you were lucky, you could actually see you could come up with a solution. I will now show you what I believe is the improved version of these functions, where everything is named a bit more appropriately. So let me put them side to side. Okay, I guess that's better. So here, I create an integrator. Okay, this is clear for everyone. Traj discrete is trajectory discrete. And beside trajectory discrete, I replace I with the full word integrator. Notice that integrator is a function defined in global scope since it's called here, but given that this is a function, I could actually use it as a local argument instead. That's a nice trick to know. Current time is a function from global scope, so I don't change it. Ttr and dt are actually time step and transient time, so this is exactly how I rename them. tv is the time vector, which I write here time vec instead of time vector. Maybe this is too short. Anyway, I continue to use transient time. Now I step over the time vector, I step the integrator for the given time step, and then I push into this container called traj, which is the trajectory, of course, the state of the integrator. I didn't want to name this full thing trajectory, even though I could, because this one is something that I believe is clear from context, because this function is 5 lines. If this function was really long, I would name this trajectory as well. Okay, the second case is something that I really like, because if you don't really know the field, you certainly cannot understand what is on the left. If you know the field, maybe you can understand it. But I'm not really familiar with the thermodynamics that well, so I renamed everything here. E, EQ, W2, WT is the saturation pressure water. So the function is saturation pressure. It gives you the saturation pressure given the a container of temperatures. It could be a vector, it could be anything. EEC water MK is equilibrium vapor pressure for the water. So that's why it's named like that. That is calculated for every temperature. The same for ice. Then I define this variable over here that says is only water, that checks if my temperatures can contain only water, which happens when you have temperature above the triple point for H2O. That's another thing I renamed. Ttr, which stands for triple point or T triple point, it became triple point H2O. Here I calculate the actual saturation pressure. That is an operation that involves the saturation pressure of ice, the saturation pressure of water, the temperatures, and the triple point constant again. And then here in the saturation pressure vector, I have to replace entries. If it is only water, only ice or so, I get the saturation pressure that I computed separately only for ice. And if it's only water, I get the saturation pressure I computed separately only for water. So I hope it is clear that you understand immediately what the code on the right does. It's not clear? Tell me why. For whom it's not clear? Yes. So the question is if the function push is the same as append. The Python append, yes. In Julia, append is something different. Push is the same as the Python append, yes. All right. So I hope you are convinced with this exercise that you should take naming your code very seriously. Okay. Next big part of this block is functions. And we start with functional programming. Functional programming is a style of coding that is particularly suited for scientific programming. What is it? Well, your code is structured around functions. Do you have a question? No. Okay, the fun, all right. The code is structured around functions. Each function performs a single specific task. Functions are reused throughout your code base, and higher level functions are composed of lower level functions. It will become clear in a moment what this means. And lastly, the function names are a clear indication of what they are supposed to be doing. Why should you do it this way? Well, it is reusable and it is intuitive. It allows for clear code, and it allows for code that is both easier to extend and to maintain. And also, very important for us, scientists are notorious for doing this, functional programming dramatically reduces code duplication, which is something scientific code suffers a lot of or from. Okay, here is the prototypical example. You have the function on the left that does these nice 3 things. It finds a suitable download location from a given ID. It downloads a sequence from a given ID, and then it does a check on the sequence to see if it's valid. You can transform this function into that function that finds the repo, downloads the sequence, and then validates the sequence and returns the protein sequence. So you see these individual code blocks that I had inside my function actually became functions on their own. Quick notice, in case someone is using a Paleolithic programming language, this only works when objects are passed by reference and not by value. Here is a very nice meme about that. If you clone the person, it's the same person. Depends if you clone by reference or value. If you don't get it, don't worry. Thankfully, you are using too modern of a programming language, which is absolutely great. Good job. Okay, so did you get the gist? Make code blocks actual functions. Size. What should be the size of a function? How short should a function be? 200 lines of code or 100 lines of code? What do you think? How many? 10. Okay, it was a trick question. The answer is 3 to 100. Sometimes you actually need 100 with median 30. The way to achieve this is to have this super useful rule of thumb. Functions should have one level of abstraction. Here is a function that has two levels of abstraction. This is the first level of abstraction, and this is a second level of abstraction. Think of levels of abstraction as levels of detail. That's one other way to think about it. This function would, in here, just calls other functions that convey their use, but then also does something detailed that could be a function itself, and then goes back to calling other functions. So this function does not have two levels, does not have one level, but two levels of abstraction. The solution here is to make this code block into a function that literally says complement or compute complement, I don't know, your decision here, that computes the complement map given a sequence, a protein sequence. So this makes the functions cleaner and outlines their use even more cleanly. And some, of course, I hope this is obvious to everyone, small functions make bugs much easier to find and subsequently solve. It's much easier if your bug is in a 5 lines of code function than 500 lines of code function. How can you know that you have to start sorting your functions? Well, if you have a lot of duplicate code, this typically means that you should be having a function instead for this code that you duplicate all over the place. Okay? Sort functions, one level of abstraction. Purpose. Functions should be doing one thing, or try to be doing only one thing, and that thing is what their name conveys. This is also known as the single responsibility principle. That simply means everything that exists in your code should have one responsibility. Here are possibly one things that functions can do, and this is a totally non-exhaustive list. They can calculate a quantity. They can plot a plot. They can search something that you want to find. They can do a specific processing of some data. They can load in some data. They can answer a question, like with true or false, etc., etc. Some possible things. If you have a function that does two or more of these things, that's another very good indicator that probably you could be splitting this function into two functions. Notice here I'm not referring to a function that calls two different functions that do two different things. That's a different story. This is how you should do it. Okay, this also increases the reusability of functions, and once again decreases the bug risk. So you see here we have the same patterns coming up all over the place. Functional programming, no matter how you look at it, decreases bug risks, increases reusability, decreases code duplication. It's really good. You should really do it. And we have an exercise, don't worry. The name of a function is exceptionally important because it is the thing that conveys the purpose of the function. It must convey clearly and without ambiguity this one thing, the special one thing that the function does. Too long names or names that are not clear enough might be an indication that the function doesn't actually do one thing but does several things. Here are some examples that I believe are good names that convey the one thing that a function does. Lyapunov spectrum that computes the Lyapunov spectrum, nearby agents that returns an iterator of nearby agents, mutual information that computes mutual information. Here I should say something. It is both my personal preference and what happens in most code that I read, at least in my programming language, that is Julia, that people don't use what I would call useless words, like I did not name this function compute Lyapunov spectrum, even though this function computes the Lyapunov spectrum. I just named it after the thing it returns, and I hope it is clear to the reader that this function will somehow compute this thing. So I don't use these words like get or compute or whatever. You might find that for you this is more readable. I don't know. That's kind of your decision. For me, it isn't. Another important thing is to not shadow functions. This means that you shouldn't use names that are names of existing functions when you define your own function, even in the case of no conflict. Here's a Python example. You could have the functions npsort, pltsort, and myPacketSort. So this is legitimate code. You could call all of these functions because you have a separation by the parent module. However, this can be confusing to the reader because since the functions have the same name, do they also do the same thing? A better alternative is to either extend the base functions, the functions that come from the same module, if your language allows this via a single or multiple dispatch, or if they don't do the same thing, then define new functions whose name better reflects the different behavior these functions have. Yeah, that's the naming. Now, here is an example of what I would consider a bad function. This because of its name. The function is called check authentication. It gets some user from a username. It encodes a password, and then does this nice operation. Can you see what is the side effect of this function? What are the two things this function does? Can someone tell me what are the two things? This function does not do one thing, but does two things. What are the two things? Okay, the first thing is what the function says. It checks the authentication of the user and returns true or false whether if the user is authentic, whatever, correct or not. But it does one more thing, which is to initialize the user session. So this function does not only check if the user is okay for this website or whatever, but also starts a new session. And this is not conveyed by the name of the function. Furthermore, this function is bad for another reason. It returns true or false, but I don't think that's the correct return value for this function. Because what does false mean? Is my password incorrect? Is there a network error? There are many other things. A better return value for this function would be a string that conveys what's happening, and you have the string successor valid if the user is valid. Okay, I think this is a final slide before the exercises. Okay, second final. Arguments. Guys, I know this is a lot of information, but remember, these are the slides that you have to keep and you have to revisit from time to time as you work in your own code base, which is the last hour of this block. The last hour is using these slides to improve your code. Remember, okay, you should try to keep the arguments of functions small, and the least amount of arguments, the better, by far, because each extra argument increases the mental mapping when people read the code. Remember, when you read the code, you need to create a mental map in your brain on how the input and output of functions connects throughout the code base. And clearly, the more inputs and outputs you have, the more complicated the map. So less arguments are better when possible, of course. Two simple ways to reduce this thing is to make non-crucial arguments either keyword arguments or passed-in containers. With keyword arguments, you have this very nice technique that is called keyword propagation technique, and to my knowledge exists for all modern languages. And here is how it works in Julia or Python. You declare some keywords, variable, whatever, and you indicate to the language this can be an arbitrary number of keywords. And this is never explicitly expanded. You never care what this is. You just propagate it forwards to more lower level functions. And there is a final function over here that actually declares the keywords and actually uses the keywords. And whatever keywords the user gave to plot field core would be all the ways go down to plot field. And this is how it looks in Python as well. That's a very nice technique. Another technique is to create a if you have, for example, an ODE, you solve a differential equation, typically you have a lot of parameters as part of your equation. The best way is to create a dictionary or whatever named container that contains the parameters, not to create a function with 20 arguments because your ODE has 17 parameters. Just make a named container and put the parameters in there. Okay. Next advice. So this is something that is not common, but not only I like it very much, it was very helpful when we were writing software that has outside external contributors. And that is to define functions in a main-like setting. where the called functions, the functions that the main function calls, are declared after the main function. Why do I like this? Because you start with a high-level description of the code base. And if you think about it, this is similar to how you structure a paper. You first give a summary of what's going to happen, and then you have detailed method sections for the individual methods. So here, when I start the code, I read, oh, okay, the main thing we want from this code base is how to load a sequence. And what this function does is first downloads a sequence and then validates. And then I can go below and see in more detail what download actually does. Let me say something clearly here. If your language doesn't allow this, you most certainly are using too old of a language, and you should really consider to learn something a bit more modern. Just saying. Maybe it's my crazy opinion. All right, second exercise, and that's an actually hard one. So we have uploaded a code file called Eratosthenes sieve. There is a Julia and a Python version. If you don't use any of these languages, simply translate it verbatim to your language. It shouldn't take so much time. Your job is to make this file cleaner and more readable by, first, using higher level syntax that your language provides. As you will see, when you open this file, it's actually not Julia or Python code, it's Fortran code written in Julia or Python. And your job is to first use high level syntax that your language provides, like list comprehensions, for example. You don't have to write a 5 lines loop in Python to create an array. You can just do it in 1 line. Then use functional programming and better naming style for the variables. And also use functions from your standard library, for example, finding the true elements in an array. Once again, you don't have to write an explicit loop for it. Every function has a function. Every programming language has a function. Go, 20 minutes. I think 20 minutes is a lot of time, we'll see. The point is to really make you work and understand things that are bad, so you are avoiding these patterns in your own code. The correct solution are many. The important thing is to avoid the bad versions. So what I will present first is how this code would be written if it was written directly in a high-level language like Julia or Python. Because remember, this was, I don't know, either Fortran or Java, something really... Anyway. So this would be the version that would be written directly in Julia, and what it does is that, first of all, it immediately initializes arrays to a specific value, so it doesn't require a for loop to create truths or whatever. We use f equals truths instead of this ridiculous thing over here. We just say f equals truths n, sure. Variables like I and j that iterate do not need to be declared. The language declares them for them, and there is no reason to make loop to count true elements in an array. That is literally what the function count does. So in the end, you see I have this function over here, count, that does this thing over here that would do explicitly. But still, this is long code, and one way to make it functional, composed out of 2 simple functions, my solution, which I will show now, just has 2 functions. It's these 2. This is my solution. The main function is called Eratosthenes sieve. The first difference is that it does not have a huge if loop that idents the entire code, and instead it has it favors an early return statement that starts at the start. If n is less than 2, immediately return integer end. Don't have a huge if loop for the entire function. So it initializes a vector called is prime. Here is the notation with the is for booleans. And it has a comment here that says number n is prime if is prime is true. And then it sets is prime 1 equals to false because 1 is not a prime number by definition. Then it calls the function cross prime multiples, and then returns primes equals find all is prime. Find all is a function from the Julia language that finds the indices of all true elements in an array. And because in Julia indexing starts from 1, the indices are the same thing as the numbers that are primes. In Python, you just add +1 and it's the same thing. And here is the function cross prime multiples. It gets the length of the is prime vector, whatever. It iterates from 2 to round integer square root. Okay, this you know what it means. It's the same as the previous code. It checks if the thing is prime. If it is prime, then for j, in 2 times I iterate with step I all the way to n. set is primes to false because they are multiples of the prime and thus are not primes, and an end, and that's it. And then you call this function with 100. So that is my, oops, what the fuck? My solution. And you will see these green things at the start of the function are just documentation strings. We will talk about them later in the workshop. Don't worry if you don't know what these green things are. They simply explain what the function does. But that's my solution. It's these 10 lines. And you see I didn't use much comments. This is something we will now go into, commenting. I will upload the solution, don't worry. Okay, what's the time? Damn. All right, I love this code. This code is amazing. Proper use of comments is to compensate for our failure to express ourselves in code. This comes from an amazing textbook that this workshop is partly based on, by the way. Why? Why are comments bad? They are not bad, but they have some problems. They are very hard to maintain because, of course, they are not code that runs. Wrong comments are much worse than no comments at all. Comments are expressed in human language and not code language, and there are much better ways to document code in human language outside of comments, which is what we will do in block 5 of the workshop. What this means is that self-explanatory and simple code is superior to complicated but commented code. Let's start with examples of comments that are clearly bad and should be avoided at all costs. The first comments are redundant, useless comments that provide no information whatsoever. This comment over here says validate protein sequence, and below is a function that calls validate sequence given a protein sequence. This comment is useless, tells you absolutely nothing. Misleading comments or incorrect comments. Here this comment says return true if all amino acids are valid. That's not what this code does. It actually errors if the amino acids are invalid. Other comments that replace actual proper code. Here, there is the comment that says tox5 contains the raw p-value, tox6 contains the test number, and then it has tox5 and 6. Replace the comment by actual code that tells you, I will assign tox5 to the raw p-value, etc., etc. That's actually what I do when I see exactly this kind of comments, and I saw them in your solution, so be careful. Redundant comments are the worst. Another thing that you really should avoid doing is commenting out valid code, runnable code. Please don't do that. For example, at some point you want to fix a bug, or you know this code is erroring or it doesn't work and you comment it out. Or you want to add a slightly modified version of the code but also keep the original code, so you comment out the original code and then below you have the modified. That's insane. That's insane. That's why we learned Git, so you don't have to do this craziness. Don't comment out code. It's really confusing. If I'm reading source code and it has valid code, runnable, that is commented, this is very confusing. Yeah. And comments in full capital are distracting and flow interrupting. That is general advice for writing text. If you read a novel and suddenly you have a block of everything capitals, that is distracting. Of course, there are very good reasons to use comments in other situations. I have examples here on the side. Comments that warn of consequences. Here it says that this test requires an hour on local machine. You cannot run this on CI. We will learn what CI is later. Comments that explain regexes or other structures that are typically unfamiliar to the average reader. Here says this regex, or this genomic regex, matches genomic regions in the format id ... start to end. To-dos, self-explanatory, justifying an operation that can only be known by knowing a specific paper. So here you write this equation that comes out of nowhere, but you say, no, this doesn't come out of nowhere, it performs this equation from that paper. Defining short-named variables in scripts. Notice that this is scripts. I told you short-named variables are bad, but in scripts I don't really agree that they are bad. Don't worry if you don't understand what scripts are. This is exactly what the next code block is about. And justifying a value for a specific choice. So here I have peak equals 7 and I have a comment, this is a good value for peak detection, I have tested this myself. Notice here there is a better way to do this by adding a string to the variable, and this becomes the documentation string of a constant global. I think that's also possible in Python, right? Is it? Is it possible in Python? Okay, approximately the same, yeah. So that's an alternative, a better way to do exactly the same thing. It still takes one line of code. You still have exactly the same thing, but now this thing is actually examinable from within the language. All right, now we go to what I honestly do believe is the best possible kind of comments. So the first thing to understand is that it is nearly impossible to comment the actual behavior of code. Only the intended. You write some code and you have some intention of what this code does, but you might have written something wrong. So it is possible to comment the intended behavior of the code. And therefore, high-level, intention-based description of code blocks is what I consider to be the best possible comments, and actually most people consider this true. This is known as commenting showing intent. And these comments simply describe what the following block of code intends on doing. These comments must be language agnostic, of course. They are written in human language, and they are always recommended to have. I will show you a quick example now from some source code from some package. Let's see it. All right, here is the code. Don't worry, you don't have to understand the code. I'm only going to highlight the comments. Here it says, okay, here we declare some internal constants because they are from the paper, and we also acknowledge that they are arbitrarily. Yes? Of course, my dear friend. Is this okay? All right. Okay, we say calculate the mean position invariance of the trajectory, equation 1 from the paper, page 5, using random samples approach or instead of direct integration. Calculate cross-distance scaling, whatever, something. Here is another nice comment. It's a to-do comment over here. Another to-do comment. So here, that's what it says, calculate this cross-distance. It is actually a really simple for loop. Here it says, okay, we perturb samples from the surface of sphere. This doesn't make sense to you. Obviously, you need to know the algorithm to understand this, right? I'm just showing what commenting showing intent actually means. Reintegrate to some time capital T, accumulate distance and square distance, etc., etc. So you see the code blocks are annotated with descriptions. That's what it means, comments showing intents. These are very, very, very good. You should really have them. But if you will follow the good practices we will be teaching in this workshop, you will actually find that you will write very little amount of these comments showing intents. Why? Because in the majority of cases, you can make them documentation strings, which, as I said, is fundamentally superior to comments. And since each function has its documentation string, and each function are small, like 5 to 10 lines of code, you will see that comments showing intent are rarely needed. In fact, for me personally, it was surprisingly hard to find examples for this slide. Of course, I was only looking in the libraries I contribute to. Obviously, there are cases where you will have to write large functions, like the one I showed you. This was a large function relatively. It was about 50 lines of code or so. And they're clearly there. These comments are very helpful, and you should have them. So these are the best comments, but it turns out, don't be surprised if you don't need them that often. Documentation blocks come later in the course, don't worry. And to make the case, here is, once again, the solution of the Eratosthenes sieve. I make it larger again, so my friends in the back don't complain. This solution has practically no comments. Yes, practically no comments because the functions are simple and their comments or the description of what the function aims to do is just above the function as a documentation string. That's why it's not a comment. All right, next. I will go quickly through these slides because I think they are just obvious guidelines that you may not have thought so far. Vertical and horizontal formatting. Outside the file, group functionality logically into files and folders. Obviously, when you write source code, try to organize it into files that make sense. My advice would be to start all your scripts with a description comment of what the file contains or aims to do. Here is a description from a file. It says styling file for the figures of the velocity blah blah paper. Another description, this file defines blah, 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 blah. Inside the file, I also put headers. So if I have sections of codes or function definitions, let's say a couple of hundred of lines, that sensibly belong to the same kind of functionality, I put a header there. A header about histograms. Oh, here is all the functions about histograms. A header about functions that find the peaks in the velocities, whatever. You should also format your own code inside the actual code file, you should properly use blank lines similar to writing a paper. Everything in the same train of thought is cohesive and therefore should be written without blank lines. However, blank lines should separate complete thoughts or paragraphs. This is a very nice example from the Pandas Python library. On the left, it's a standard paper. This is just a paper. It has a couple of paragraphs. And on the right is just some code, but you see it is the same thing. It has some paragraphs. Each of these code blocks is cohesive. It doesn't have any flow interrupting empty breaks. There are interrupting empty breaks when you go to another paragraph or to another train of thought. Very useful for reading code. Horizontal formatting. You should always have your lines in your editor to have a maximum length and use your editor to actually enforce this. So there should be a line in your editor. You see this line over here? This line is 92 characters. There are some common lines, how many characters it should be, 80, 88, or 92. Doesn't really matter. It's important that you have one. So you shouldn't have editors that wrap lines of code. So if a character exceeds the editor, they erupt. Don't do this. Why? Because line break in programming is meaningful. You cannot just randomly add line breaks and code would not work. Therefore, you want to reflect this when you read the code itself. White spaces are typically defined by the style guide. Here are common cases. All binary operators should have enclosing white spaces except of multiplication, exponentiation, and division. Here are some examples. Two things that so the reason the third thing is more readable than the other two is because that's how we write math, typically. It's just a convention. The same thing on the right. I think the second line is much more readable because it puts white spaces among all operators except the division operator. And one more thing is that you should always have spaces after commas and semicolons and spaces between assignment blocks. Now here is something that can be debated. So if you do an actual assignment, you should always have spaces, no matter what. Like here, I assign to A, I have spaces between the equal sign. One thing that can be debated is whether you should have spaces when you do keyword assignment. So now I say what the value of the keyword Z is. And here, depending on the style, some people prefer to have the spaces, some people don't prefer. As far as I know, this is typically the preferred in Python, to not have spaces, because it separates keyword assignment from value assignment. So this, check your style guide, I'm not sure. But the rest, I'm pretty confident you should follow. Each code block, okay, I think everyone does this already, so there isn't much to be discussed. Each code block should be idented. So when you start a for loop, ident it with 4 spaces. If you start an if statement, ident it with 4 spaces, etc., etc. Something that not everyone does, but they really should do, is to always write the float point literals, including trailing or leading zeros. So instead of writing, where the mouse is, instead of writing something like this, write something like this. And this is the final slide, right? Oh my God, amazing. All right, so far we have discussed advice on how to write clean code. This advice is obviously very important to follow. It is equally important, though, to be consistent, first across the file, then across the repository, so the code base, and then across an entire organization. Okay, the last part doesn't apply to you. And therefore, it is strongly recommended to follow a style guide, and if possible, incorporate an automated formatter to your code. These are programs, sorry. A formatter is a program that reads your code files and does some automated formatting processing. And it is even more strongly recommended that you all agree in the style you want to choose. And here are 2 recommendations for formatters that you can find in the slides, one for Julia and one for Python. So these are all the advice I can give you for clear code. And now for the rest of the time, you can do whatever you want, of course. My advice would be to try and apply all of these guidelines to your own code base that you brought here with you. Start with organizing your files, then go into your functions and start establishing good naming conventions, your sensible names. Separate your functions into smaller functions. Go through your 500 lines of code functions and try to make them 50 lines of code functions or less. And after you're done with this, remember you do this in a branch. So you branch in Git, start working on cleaning your code. After you're done, you can merge your branch, bind into the main branch, and add a tag as well. Make this tag name clear. Remember, we add tags with git tag, name of tag. That's it. Start working on that, please. Welcome to the third and final session for today. Just try to pull through. Don't worry, we'll make it. Everything is fine. This is a really interesting section because I believe it will teach you things that you really have not really had the chance to appreciate fully. Yet I promise you, this section is the one that will most likely have the most positive impact on your workflow. That's my belief, at least. So we will discuss incorporating software development paradigms into the scientific workflow. So let's consider for a moment some differences between a typical scientist and a software developer. On the science side, you would have someone that mostly writes code for themselves, copy-pastes 100 lines of code just to change one line of code, doesn't really have taken any lectures on writing good code, and typically is not very good at optimizing code, but it is very good at inventing algorithms. On the other side, you have someone that what? A person like? Okay, I'm very sorry if you feel personally attacked. That's exactly the point. So a developer would write code mostly for other people, would try to write minimal and extendable code, has certainly taken lectures or guidance or mentoring on writing good code, knows how to optimize code, is very good at designing APIs. We will go through what this means, don't worry. And of course reads R Programmer Humor, which is likely the best website on this universe. As a scientist, you really want these skills. These skills are extremely useful for you for the reason that I will highlight in 2 slides from now. So, the most important thing, or not the most important, the first thing that you have to do is separate low level and high level. What does this mean? And I actually call this source versus scripts. That's the best way to keep it in your mind. So if you look at the typical project structure, you would have something like this. You would have some scripts and you would have some source files. The low level, or the source, is where you do your hardcore computations. You generate data, you optimize code, you have functions and structures that are used throughout the code base, you have plotting recipes, you have data analysis pipelines. Everything in this low level is of general use and reused. There should never be reasons for code duplication in the low level. On the other hand, you have the high level, which are the scripts. These are running or submitting simulations. They are listing or loading results. They are visualizing. They are doing analysis to specific data. They are creating notebooks for presentation, whatever. High level or scripts should never define new functions methods, or most of the time they don't have to. So another way to separate these things mentally is in the sources where all the definitions happen. In the scripts is where you call these definitions to actually do things. That's one way to separate them. In my opinion, the user of the code should only see the low-level part of the code when either adding some kind of low-level functionality, so a new functionality, or fixing a bug. Never for copy-pasting something from one file to another file. So source must be crystal clean. So clean, your mama would be proud for saying it. Okay? Now, if you think, but this isn't really possible in a real science project because, of course, science is sloppy and blah, blah, blah. Also, you know how I applied these guidelines in a project I had 3 years ago. And it's called Velocity MTD. It's about correlations in timing intensity in music performances. So I will show 2 files from the source and 1 file from the script. Let me find this. Oh, damn it. Okay. What did I say, the files? Correlations, yeah, sure. Okay, so here is one file. This is a source file. This means it defines things, and you see it has a nice top-level description of what the hell is going on in there, definition of measures of cross-correlation and power law correlation. Some using statements, whatever. Here is a function that is defined, mutual information. It does something, probably you can imagine what it does. It calculates the mutual information. Some other functions, some function to get a normalized Pearson coefficient and what is called confidence interval, whatever. Some other function over here, another function that does binning, another function that gets a correlation intervals, whatever, another function that does something else. Other example, what was the other example? Well normalization, great. Another source file over here contains functions for processing velocity histograms, smoothing them, whatever, blah, blah. Some function that gets the histogram of the velocity from some nodes, some other functions that get histograms from different nodes, a function that smoothens a histogram over here. Yeah, functions that smooth a lot of histograms. Some function that finds peaks in the histograms. Aligning peaks, whatever. Oh, okay, I think that's even a typo. Align isn't spelled like that. Anyway, you get the gist. These files just define functions that are useful for me in this context, in this scientific project. And then you have something else, the scripts. What script did I have to show? Drum scatter singles, sure. The scripts now use these functions. So what I'm doing here is I'm including files from the source directory. This is exactly what this function does. It includes files from the source directory. So I bring these definitions of functions into scope, and then I want to plot something or analyze. I use these functions to get a MIDI file, do whatever cleanup I have to do, estimate whatever stuff I have to do, and then do whatever things call other functions, start plotting, start plotting by calculating this mutual information business or whatever, blah, blah, blah. What is really important to notice in this file I'm presenting right now is it has only one level of abstraction. This should be every script you write. Every script you write should have one level of abstraction. This is it. You see, every single line just calls a function or just a trivial, well, trivial depends what is trivial, but a simple computation. I don't have anything complicated over here, a complicated analysis. This goes into the source code. Is this clear? A what? Yes. A good rule of thumb I follow is that every indentation you have that isn't because of a for loop is already a new level of abstraction, probably. So think of something that you could describe in a sentence, like, for example, calculate the mutual information. So this is something well-defined. The mutual information is something well-defined. However, to actually do this in code, you have to do several steps of computation and several manipulations of data, right? Yes? That is the first level of abstraction when you call the other functions. There is no such thing as zero level of abstraction. There is the first level of abstraction. Sorry? What function is that? What exactly does it do? Does it do 1 plus 1? So plus is not a function for you? What is it? Plus is a function. There is no such thing as functions that don't call other functions. Okay? All right. This exercise, I hope, will make this thing a bit clearer for you. So this is the first exercise for this block. You are given a script called plot time series monolithic. There is a Python and a Julia version. What this script does is produces the plot that you see. And what you should try to do is separate this into two files, a source file that contains function definitions, and a script file that includes these function definitions and just uses the functions. So try to identify the building blocks of this script, so the things that the script does at the conceptual level, and isolate these building blocks into functions, and then simply code these functions into a simple script. The final result should not really be more than 20 lines of code, the final script, okay? So I'll give you 10 minutes for this exercise because I think it doesn't take much time, and then we can discuss the, let's say, the solution, okay? 10 minutes, let's go. And hopefully this clarification on source and scripts will become clear. Remember, source only defines, scripts only computes, includes and computes. That's another way. So, where are we? Block 2, sorry, block 3. We are in block 3. Plot time series monolithic, sure, let's see. Plot time series monolithic source. Plot time series monolithic. Oh shit. Where is the script? Plot time series script. Great. Okay. Time series monolithic script. All right. So the thing that you all did very well and correctly is identify the building blocks. What? All right. Anyway. So correctly, you identified that there is a part of the code that calculates the moving averages of some time series. There is a part of the code that calculates NRMSE, which starts for normalized root mean square error. Some part that calculates the trend. So your job then is to simply make all these parts functions. You need one function that calculates the moving average of a time series, one function that fits a trend to a time series, one function that calculates the error between two time series, and okay, and then you have the plotting part. One thing that I saw almost everyone do, and that was really interesting for me, is how you created these functions. So here, for the moving average, you made a function that already took as an input a vector of time series, so several time series. However, the best way to do this is the other way around, to have a function that calculates the moving average of a time series, and you simply create a list comprehension over this function. So what does this mean? This means here that I create this function called moving average x, w, with w the window size. And you see here comes the x part, the name. What x is meaningless for moving average is whatever the caller wants it to be. So here the name is meaningful only in the caller, so I call it x. And it calculates the moving average of this time series x, right? In the code now, I only have to broadcast or loop over the time series I have. So over here I have this line now in my script that says, the moving average versions are the broadcasting of moving averages. So for Python users, this is exactly the same as typing average equals moving average e, w for t in time series. So this is exactly the same. It's just that Julia has a simpler syntax for it. Okay, I apply the moving average to every time series. I don't get a vector because remember, we want the simplest version, the most bare-bone version of every concept. And we build on this simplest possible building blocks. And the same story happens with every part of the code. So we have here the source. It defines the moving average. It defines this fit trend function that takes as an input a time series or two time series, x and y, and fits a trend into them. Same thing with the NRMSE, however it's called. I didn't create a function for the plotting part, because I felt it wasn't necessary. I simply loop over the time series and I do the same thing for them. If this was a meaningful process, a meaningful sequence that you would do several times in your code base, then yeah, go ahead and make this a function as well. But the crucial part is really to understand the computationally building blocks, moving average, trend, whatever, make them a function. Put them in the source file. Here is the source file. At the start of your script, where is the start? Include the source file. This brings into scope all the definitions, and this is what yours. And this is you're done. This is how you separate a file into source that defines the building blocks and script that uses the building blocks and has one level of abstraction. Let me show this again, because it wasn't clear. Is it clear now how this script has one level of abstraction? Is it clear now that how this script has one level of all right, perfect. Great, we move on. Next part, design a high-level API for your source code and use it. All right, let's get through what this means. If you have some kind of source code which does not do anything by itself but only defines things, then you need an application programming interface. This is really fancy words saying that's how you use the source code. So what you want to do then is think first. First think on paper or in your mind or wherever. How would you like to use your code to obtain results? And think ahead. What kind of extensions do you expect to encounter in your project? And then think, okay, did I design this API, this set of functions I want to have usable for me to use in my project? Did I design this to be general enough, according to the extensions I can imagine? Then, after you have thought this through, you actually go and write it. And then you ask yourself the following questions. It's like a quality control. Is it minimal? Did I write more than I had to? Is it extendable? Can I easily add more functionality to this code base, or is it a pain in the butt? Is it modular? So is it composed out of individual pieces that I combine together? And of course, think also about clarity. Is the way I thought about these processes understandable and simple to reason for logically? Maybe it has arbitrary restrictions that it should not have because I only thought about my specific use case and it restricted me without real reason. Yeah, maybe it's too specific to your setting. Pro tip, try it so that there is only one way to do something. Similar ways to do something should do some amount of setup and then call this one way to do something. At least in my experience, having one way to do things is better. Now, if you think about what we are doing right here, we are embracing the duality of our job. Because at one hand, we are the user of a code base. We want to use a code base simply and write 5 lines of script and do our analysis straightforwardly. We don't want to write 500 lines of script. But on the other hand, we are the ones that actually write the code that we use. So we wear first the hat of the user to think about what we want, and then we wear the hat of the developer to do it. And unfortunately, remember, you are both of these things. So you have to embrace these 2 steps and, yeah, just do them. Okay, so I hope it was kind of clear. So let's try and apply this now in an exercise. So let's try to design an API for monthly means. And if this is too difficult for you, we have a second exercise that is moving averages instead of monthly means. So this is the process we want as a user. We have a vector of values and a time vector that accompanies the vector of values. So we literally have a time series, but the time vector values are actual date instances, right? And what we want to do is aggregate or average our time series over months. So for all dates in the first month, the values of X are averaged. Then we go to the next month. For all dates in the second month, the values of X are averaged and blah, blah, blah. Okay? The function then returns M and Y, with Y being the means of this X time series, and M being a new time vector that has only as months the time points. If you're not familiar with handling date types and you think this is a bit tricky, the next slide has an exercise with running means. Just look at it yourself. So you think this is what I want, okay? Then you write. Then you say, okay, let's write the code and ensure it works by testing it with the very simple case of having a daily time series where the value at any date is the month of the date. So if you have a time series in November, the value of the time series would always be 11. In December, the value of the time series would always be 12. Okay? Test it with something like that. After you have written this part, which I hope will take you 10 minutes, fingers crossed, then we go to the second part, which is actually making an API that is really, let's say, generalizable. So what is the most reasonable extension you would expect to have in such a code base? Well, instead of monthly averages, you might need yearly averages or daily averages, where you aggregate over a year or over a day, etc. Instead of a mean over a month, you might want the standard deviation of the quantity over a month, or other moments, or whatever. Is it possible or straightforward to do these extensions with the first version of the code base you wrote? If not, what changes do you have to do to make this possible? And let's say the most hardcore test you would apply to this API or this set of functions would be calculating summer and winter averages by defining as summer to be the months that are in 3, 4, 5, 6, and 7, and 8. Okay, and if this is too hard, just do the next slide, which is pretty much exactly the same, but for moving averages, okay? I just want to spend a bit of time just discussing the solution that I wrote, which, let me find the slide, sorry, which cannot be the solution you came up with because this is already highly advanced, but it is still useful to highlight to you how you can make code that is still simple yet general and applicable without any weird or fancy structures or using many library functions. So this is the function, this is the solution of the first exercise with monthly means in, let's say, the naive way, the way that does its job well, but only that job, just calculates monthly means. So I have this function over here called monthly means that takes as an input a vector of dates and a vector of numbers. And it takes as an argument a day number, which would be the day it will assign to the new vector that has the months. So because you are averaging over a month, but which day of the month you put in the final date, no one cares. Or maybe they do. Anyway, it does some simple assertions over here. It checks that the time vector is sorted, and it checks that the day number is less than 28. It identifies the first date of the time series, of the time vector, and the final date of the time vector, and then creates a new vector of time that is literally the start date, and then time step of 1 month, and then the final date. Okay? So this is kind of set up. By now, it isn't the actual juice of the function. The actual juice of the function is this function that aggregates over the same months. So the way I thought about this, I was like, okay, let's start with the month we have now, and we iterate through the time vector, and we calculate the month at every point. And if we switch month, or if we change month, then we know, these are all the points that are in the same month, and then I average them. And then I continue the loop in the same process with the second month now. At every time I check the month, I keep track of the month. If the month changes, I know this is the point I have to stop my averaging process. So that's exactly what's going on. I start my output, which is zeros by default. This is the first index in the month. And this is the current month. So remember, M is the time series, or let's say the spatial vector that is already blocks of months. So I go through and I pretty much do the process I described with English words, but not with code. We don't have to go through the code because you don't know Julia, and there is no reason for me to explain you this code. It does exactly what I said with English words. I hope you trust me that it does exactly this. But now when we think about extensions, there are many things in this code that are hard-coded and I cannot change. For example, these ranges are already months, and I cannot say how I average and all these things. So if I really wanted to have something as general as the second part of the exercise, I would have to rethink some of the things I did. So now I will show you the code that would do the second thing of the exercise, which would be any kind of averaging for any time, any kind of time window, in any kind of function, and everything is any kind whatever. And the key thing that you could realize there is that by splitting things up and making less assumptions about the input, you actually would get a lot of these things, let's say, for free. So just by writing instead of mean, whatever the word aggregator, you already allow the user to give you this aggregator, which for the user could mean the mean function, or it could be any other function the user wants, like standard deviation. That's already a simple choice you can do, which immediately allows you to aggregate in other ways besides means. The other thing that I did here was to allow for, let's say, any kind of range or temporal range I can iterate from. And the way I did it is I allow the user to give me a function that when the function takes a date, it gives me a number. In the previous case, this function was just the month function, that given a date, it gives me the month of the date. So it gave me 1, 2, 3, all the way to 12. Now I allow this to be any function. And what I do is I actually simplify the code now. And what I do is I just collect the ranges of indices that belong to this same info function. So if this info function was the month, I would get blocks of indices that are just in the same month. If this info function was the year, I would get block of indices that belong to the same year. So if you think about it, in some ways I actually simplified the code. Well, I didn't actually simplify it, I made it more abstracted. I made the code have less assumptions about the input style. And by doing these less assumptions, and you see this is actually the whole code, these 30 lines, many of which are comments, but by doing this, let's say, abstracting assumptions about the code, I made it possible to do these things. So the take-home message for this exercise, and I again repeat, it is absolutely impossible for you to do this thing in 30 minutes, right? I have done it many times in my life, and still it would take me more than 30 minutes. What I want you to take as the key message here is that try to abstract your code away from the exact specifics of the point in time you want to apply this code at. Like maybe today you want the monthly means, but it doesn't mean that you really have to write a code that is only for monthly means. Because if you think about the processes, if you just abstract away the monthly part into some general function that is whatever the hell I want, the rest of the core code doesn't really change that much. So you can, of course, study this solution if you want more later, but this is the gist I want you to take away from this exercise. Abstract away whenever you can. Typically, the main reason the scientific code is really not that generalizable is because it's written with the context in mind. So if you take the context away, suddenly things become easier to generalize. It of course takes work, right? Obviously, it would take work to write this, but once you remove the context-specific parts, at least you free your mind to do these things. At least I hope. I don't know. That's what I think, right? Whether what I think is the truth or not is a different story. All right, now we change topics a bit. This is a nice meme. Some guy tries to find what day it is, and this block of code was given that gives you what day it is. Unfortunately, for one user, it doesn't work. For another user, and it works every time. So the gist of this meme is that there is some sloppy code that does a specific thing that you wanted at a specific context and time of day. But because you had this lack of context agnostic viewpoint, this forbade you from seeing the problem with the code. And now we come to how you solve this difficulty. And one of the main benefits of having source code is that you can write unit tests. Because scripts are by nature one-time things, but source is reusable. And because it is reusable, you really want to ensure that it does what it's supposed to do, and it continues to do this as time progresses. And the best way to ensure this is to write what are called unit tests. Unit tests are small pieces of code that run and check the output versus an expected outcome. They help you identify potential bugs or inaccuracies because of testing in context-agnostic situations, or more situations than what you currently need the code for. They give you confidence that your scientific results are numerically valid. They can be automated, which is what we will learn tomorrow, and ensure that everything that used to work still works, which is really cool if you think about it. Here I mentioned something that is called test-driven development. This is another style of developing code where one first writes the tests for the code and then actually writes the code. I don't do this myself, but many people do, so give it a try. Maybe you like this style a lot. I don't know. So how does this work? Well, every language has an infrastructure to do tests. These are the examples of how you would do this in Julia or Python. But the gist of the story is you write some simple operations or some simple functions that either test or assert one operation, a Boolean operation. So this has to be a Boolean operation, but of course what you test is what your functions do. So if my function was the plus function, that's the test I would write. But of course, you would actually do this for a real function, right? And so that's the basis of this story. You write Boolean checks and then you assert or you test that these Boolean checks pass. I will discuss properties that make good unit tests, and then I will show you examples of the tests for the exercises we let's say we just tried to hack together. So what makes good unit tests? Well, the first thing is that they should be unit. The unit means that they are atomic or self-contained. So each test must really test one thing, and then when the test fails, it really should pinpoint the location of the problem, which is the one thing the test tests for. There are alternatives where you test entire processing pipelines, and these are called integration tests. But in my opinion, this should really be done only after the unit tests are already covered, and if the resources allow for this. The other thing is that they should test known output or be deterministic. The best tests, in my opinion, are the ones that are defined through minimal examples that the result is known analytically. Of course, sometimes random number generation is necessary, and in these cases, you can either test a valid output range or use seeds for your random numbers, something that we'll discuss later. Robust are tests that test that the expected outcome is met and not the implementation details. So you don't want to test how the function does the thing. You want to test that it does the thing. Detach the test from the internals as much as possible. High coverage is a nice word that simply means that the more functions of the code base are tested, the better, which is obvious. I don't even need to say this. This is something I learned too late in my life, unfortunately. Clean slate means that every test file should be runnable by itself. It should not rely on the global state neither before the test or pollute it for what happens after the test. Okay, that's also obvious. Fast means use the minimal amount of computations to test what is necessary. So if you have a test that does something with a vector of 100 numbers and it works, you don't gain benefit for doing exactly the same test with 1,000,000 numbers. That's not the point of the test. Unless, of course, there is some extreme specificity for the algorithm that changes fundamentally if you go from 100 to 1,000 numbers. Regression means that whenever you encounter a bug in your code and you fix it, you should add a test for this code base, because the reason the bug exists is because you didn't test for it, so now you test for it. Yes, please. Can you explain which part? The clean slate. So this is again in the spirit of being well organized. Typically, if your code base becomes larger and larger, at some point you will realize it makes more sense to you to have different files in your test suite. So one file that tests X functionality and one file that tests Y functionality. If you are like me, the way I did it in the past was define something in the first file and then reuse it in the second file. That turns out is a bad idea. I learned it the hard way. Well, there are several reasons why this is a bad idea, but one of the reasons is that you want your tests to be self-contained because this makes it easier for you to pinpoint the problem. The more often you have to change files to see where things are defined and whether this thing that was defined was mutated in another file, etc., it just makes the process slower. It's not really like a fundamental limitation, it's just a much more convenient way to have it this way, so that other files don't pollute other files. Just from experience, that's what I found. And for some people this is obvious, for me unfortunately it wasn't. No. Now we are in a third folder. So we have the source folder that defines the code base, we have the script folder that does your science job. Now we have a test folder. This is where you would write some like scripts that actually test your code. They would look like what I had before. Now we are in a different aspect of your scientific journey, right? Testing your code. That has nothing to do with the scripts. Okay. Here is an example of what I consider a really good code test, and I didn't write it myself. I just mentioned there is a technique called recurrence plot. It just takes a time series and transforms it into a matrix encoding recurrences. You do not have to understand what this means or why it's useful. And then you can do some further analysis with this. So this is how it looks like, you see. And the question is, how would you test this to ensure that that my functions that take as an input this time series produce this nice plot correctly? The bad way to do this would be to have a saved time series, and then you create this recurrence plot from this saved time series, and then you write tests that check that what your code base computes matches what your code base itself has computed. So for a given time series, you get the output of your code, and then you just test that the code gives you the same output for this time series. So this is kind of a meaningless test, because the only thing that it tests is that the interface doesn't break over time, that you call the functions and the functions do the thing that they did in the past. But it doesn't test that the code actually works, if you think about it. The great test here would be to write down a really small such matrix, a matrix that is just 9 by 9, 9 by 9. This is like 1,000 by 1,000, just a really tiny one. And then just by hand, calculate the things that this code base is supposed to calculate. Then test your code base versus exactly these things that are calculated by hand. Now you're sure that you're testing not just that the interface doesn't break, but the code actually does what it's supposed to do. Well, here is the link to the code, but there is no reason to use it. I hope my description was clear enough. Was it clear enough? The description of what happens in this test? Yes? You test the functions of the source code, but you apply them to actual data or numbers. Yes, I mean, you can call it a script. It is a Python file or a Julia file. You can call it a script if you want, but I call it a test file. It is a file that has these operations that I showed before. Let me show them one more time. Actually, let me just show this file. That's the simplest thing I can do. So this is a file. You can call it a script if you want. I call it a test file. It looks like a script because it imports packages and it defines some things, and then it calls the functions of the package and computes some things. But then what it does, it tests. It tests that everything the package computed is exactly what I expect from my analytic calculations. I mean, you can call it a script, but calling it a test file makes more sense to me. This is not related to the scripts because this doesn't do your job. It doesn't produce your paper plots or anything. This just checks that the code you have written is good and you can trust it. That's the purpose of these things. You can use it as a what? You can use the data directly to test it. Yeah, no, that's a terrible idea. No, you should never, ever test your own science. You should test things that are context agnostic. They have nothing to do with your job. You cannot be biased by them. And most often, do the minimal tests, the tests that are simple operations you can resolve analytically. Most of the time in science, the operations you have to do are too complex to resolve analytically. But here, they aren't. So definitely not use your science data to test. Definitely not. Terrible idea. Like 2 weeks ago, I realized I gave a presentation with wrong plots because I did exactly what you just said. So yeah. So writing tests is a difficult job, but we should all do it. That's a nice meme about testing, which actually relates to what you just said. So here someone tested ordering beers and used any possible input, but then a real customer walks in and asks where the bathroom is and everything collapses. So try to be general with your tests. Don't make them specific to your context. Okay, so here we would go through the exercise of running unit tests for the monthly means. The reason it's good for you guys to go through these tests is because I tried to make them as complete as possible. So I tried to really write tests for every situation I could think of, just as an example to highlight. So I wrote tests that ensure that the API, so how I expect to call the function, works. I wrote some tests for standard ranges, like ranges that have a specific sampling time, like 1 hour or 1 day or whatever. Then I tried to write tests for data that are already monthly averages. So in this case, the function should already give me what I give it, because if I give a function to calculate monthly means for data that are already monthly means, it should give me the same thing out. Then I wrote tests that actually do actual real averaging for arbitrary real-world data. And then I wrote tests that do aggregation with different kind of aggregating functions, like standard deviation or whatever. So if you start writing tests for your own suite, that's a good example file to visit and see how it's structured. So the question is, if I suggest to write unit test for each function, I would say, yes, I actually would suggest that you write several unit tests for each function. Try to test it from as many different approaches as you can. Guys, obviously, it's about balancing time. Of course, if you have the time to devote it, you do it. If you don't, I mean, you don't, and then you pray that your code works without testing it. But I mean, it is a bit dubious to not test. Okay. One of the most important aspects of modern software design is modular software. So if you turn out to write a package that you want to publish to the world, my best advice would be really to try and make it modular. What is a modular software? Well, it is a software that is composed by individual and smaller components that combine together to yield the whole. Each component is self-contained. It has a purpose on its own, can be instantiated on its own, and if sensible, of course, it depends on the context, but if sensible, could even run on its own. And the way the components are defined and they combine together is declared by something that is called interfaces, which I will explain in a couple of slides. Here is my opinion of how a modular software really should be. From a user standpoint, you should really combine things together as effortlessly as when you describe them in human language. So it should really take only a few lines of code to actually combine the parts together, and the bulk of the code should only be in the instantiation part, so defining the options for all the different parts. This, of course, will take a lot of lines because there are a lot of options. But to combine them should really be as effortless as just passing one of the components to another component. This is really useful for science and for scientists because a modular software helps the user by allowing them to focus on the composition, which is which parts they use and what configuration options should each part has, instead of putting them together. Right? So focus on the science, not making the software run. So if you imagine that you had, for example, a planet, an aquaplanet, and someone wrote a truly modular aquaplanet, and you wanted to run different aquaplanet experiments with different surface types or different ocean types, in a truly modular software, you would literally just decide a basic class or a basic type or whatever called slab ocean, or however people call these different configurations. And you would literally just pass this thing to the main core icon or however it's called. If this was truly modular, that's exactly how you should do it. And if you don't believe that this is possible, I absolutely promise you most modern software are exactly like that. I will show you two quick examples of software that do this, to my understanding, perfectly. The first is this one. It's called agents.jl. You don't have to understand what it does. It is for agent-based modeling that we don't care. What is important is that each of these boxes are each of the modules of the software, and the user can truly and arbitrarily decide anything for any of these boxes, and it doesn't really affect the user what happens in the other boxes. The user decides the boxes, puts them all into the software, and the software says, okay, now we can do your simulation with the stuff you decided, with your boxes. Another example is Conrad, which many of you already know, which works practically in the same way. You have boxes or modules for your lapse rates, or how clouds would work, or how your humidity would work, or how your ozone would affect your simulation. You decide the boxes, you plug on these boxes on the central, let's say the core of the software, and then the software can run your simulation. So your job as a scientist is to think which decisions here should be done and which decisions make sense to be done together, not whether it would run with the software. Okay? That's what modular software is. Now I said that this design of having modular software is best executed by interfaces. Let me check the time. What are interfaces? Sorry. An interface is a set of functions that types or classes must implement to be part of this said interface. And this set of functions logically gives you the functionality that makes these objects part of the interface, and the functionality that allows the objects to modularly connect and be used by a larger ecosystem. So the simplest way to say what I just said is the input and output of the interface. What do you expect to come in and what do you expect to come out? So defining the interfaces most of the time boils down to really thinking very well what is the input and output. And one of the best parts of modular software is that it, in quotes, forces you to design good interfaces, because without good interfaces, the design simply doesn't work. And this is really nice. Now, a good tip I can give you is that function-based interfaces are better than class-based interfaces, mainly for two reasons. You can define new interface functions after the creation of a class. If you have class-based interfaces, everything goes into the class creation and therefore cannot be altered after class instantiation. Second is that you can define fully independent classes or types that adhere to the same interface. So there is no reason to inherit information as long as you satisfy the same set of functions. I would strongly recommend you to watch this presentation, which for me was very illuminating on how or why this function-based design is better. If you have some free time and you want to learn something about programming, I strongly recommend this talk I have over here. For me, it was really illuminating. Okay, we're almost at the end of the block. I'll give you my slice of life and why I think you should really consider these things I presented. So by night, I do software development. Has this affected my science, my actual daily science job, or was it just a hobby? Well, it did affect my science job positively. It made me understand some really important things. The first is that documenting my code well, or making my code clear, is extremely important for my own future self. I am much more productive about code bases that I took seriously and really tried to develop and make them, let's say, a package or whatever. Designing good APIs makes both me and my co-workers work faster. I found this especially true to be with students that we worked on the same code base. Complicated code with many functionalities can actually be written in little lines of code if you really are serious about it and you put your mind and work. It is not true that something that does many things must be complicated. That's not my experience so far. That's something amazing that is true for everyone, even though most people don't believe it at the start. People want to use your code and people want to contribute back. Most people don't want to start from scratch. They would much rather start from something existing. So if you really put effort in your code, I promise you people eventually will absolutely use it. Yeah, that's nice. Making a code base a proper package, so having this whole source business and testing it properly and documenting it makes me secure about my own projects. And this is really important. I'm sure most of you had at some point in your life doubts because you realized that something you did, you fucked up and it was wrong, and you were computing the wrong things and you were showing the wrong things in your supervisor all the time. It had happened to me, for sure. And having a code base that is like proper makes me much more secure about these aspects of science. And lastly, documenting my code really makes me know my code better and knowing its potential. So it really gives me more ideas to document it well. All right. Now you're like, okay, that's nice and all. How do I get all the skills? Well, you know what's coming. There is one way, and that way is to practice. You should think of coding as a craft. I really like this word, craft. Coding is a craft. It's like an art. And you don't learn music by buying CDs, and you don't learn painting by buying paintings. In the same way, you won't learn coding by just using existing libraries and only using the functions of these libraries. You actually have to write source code to get better at coding. There is no other way to my knowledge. So write as much source code as possible, try to improve on it, try to reflect on it. Try to write your own versions of library functions that you already use. That's good practice because you know that there is already a solution that you can check if you reach a dead end or something like that. And in my opinion, and this is how I learned coding, is contribute to open source. You get mentoring in exchange for your contributions. So your contributions are not for nothing. You really do get mentoring in return, I promise. So that's a nice meme for closing. Code I wrote today, code I wrote 1 year ago, your life after this workshop. Okay. Now the point is to try and apply these principles to your own code base, which I understand is very hard and most certainly not something that you can do in the 30 minutes that remain. So Don't worry, but this is kind of the idea in all of these exercises. The goal is that you keep these principles, you try to have them in your back of your head, and you iterate, iterate, iterate. So the first step I would do if I were you is first think if my code base operates on this source and scripts principle. And if not, make it by implementing an API. Remember, API is just a fancy name meaning the functions I use in my scripts, right? So try to make your scripts have a single level of abstraction. They just call existing functions. The functions have a specific goal. They do a specific thing, and I just use these functions in my scripts. If you have the time, of course, try to write a test suite for your code. Make it good in the sense that it really is a unit unit test, so they test small specific functionality. So if a test fails, you know that's exactly the problem. This line of code is why the test fails. That's the ultimate, let's say the best ideal unit tests are the ones that would give you the line of code immediately, which is of course really hard. And after you have done all this development, you can add a new tag in your code base, and we start from this tag tomorrow. Once again, I repeat, I strongly recommend to write tests. I know not everyone has the time, it's hard, and etc. But yeah, you would be surprised how often you have coded something wrong without realizing. Yeah, so that's today's session done. All right, vamos. Welcome people to this nice, lovely day and the nice, lovely section block 4. So today's blocks are about using our code with other people. Yesterday's block about us improving our own code and being happy with it at some point in the future. Today is about other people being happy with it. And wait. That's the wrong section, right? Correct section. That's the correct section. This is where we start today. Apologies. All right. So today we will be doing everything in teams. If you're sitting solo, you have to relocate so that there is someone sitting next to you. And we start with how we do code collaboration the modern way. Not the old school way, the modern way. So hopefully we will learn something that we can apply in our jobs every day. Okay. We've learned about Git yesterday and how it allows you to have a history of your code. This software has also the concept of a remote. A remote is simply another instance of the code base or of the repository that is in a remote place, which typically is somewhere online. And of course, several of such remotes can exist at the same time. For example, or typically they are forks of some original remote, which is something I will describe in more detail in a moment. But the story of the situation is actually really simple. As you recall, we have these nice 3 areas. First, we have files that we edit, then we stage them into this staging area by git add, and then we commit them into the local history with git commit. Now, once we want to communicate the local history with the remote history, we have to use these 2 commands that are git push and git pull. Of course, before you do this, you first need to establish a connection, which is called tracking in the language of Git, between which remote repository to communicate with and specifically which branch. So this is done again with the checkout command, but now you add the flag called track, and you give this flag the repository name, the remote of the name of the remote, and optionally the name of the branch in the remote you want to communicate to, because you don't have to communicate with the same name branch. Of course, it is clearly best practice to use the same branch in the remote and locally, but you don't have to, okay? And with the command git push, and once again specifying the remote name and optionally the branch name if it is not the same, you push your local state into the remote state, okay? So this is how you establish the connection typically. There are other ways, of course. And once you have the connection established, once again, you use push to update the remote with your advanced local changes. Or if the remote has advanced changes that you want to bring into your local case, you use the pull command. So you pull the changes from the remote or you push your changes to the remote. So I hope the wording makes it kind of intuitive how it happens. So, and this is really the basis. If you have questions to this one, we have to resolve them now, because everything else relies on you having an understanding of this. Of course, we will have exercises on this. Is it clear? You push your changes to the remote, that is somewhere else out there, and you pull changes from the remote to you. Right? Yes? So Git has a configuration file that has some kind of global configuration for you. And based on this global configuration, Git sometimes can find these things automatically for you. But it is not guaranteed, so yeah. And of course, there are cases where there are two different remotes and you want to make a choice of which one to track. And there you clearly have to use the track command. All right. So there are many services that can host Git repositories, that can host the remotes for you. Of course, you can also host them yourself somewhere else. However, here in this block, we will really be using and discussing GitHub, which is, in my understanding, the most popular of such services. And it has many useful features to facilitate code collaboration. For example, issue trackers or ways to comment on code, project management tools, labeling, automatic testing, and documentation hosting. So it has a lot of good stuff, a lot of useful stuff. And it is completely free. So my take is that this is really something absolutely amazing. This has helped my, let's say, development process very much. And it is actually where modern code development takes place. Most of the things that you know, Python, Julia, VS Code, for example, are all developed on GitHub openly. So this is really where modern code takes most of its shape. Okay, but now let's be a bit real at the moment, because if it was so simple that you just have git push and pull, then anyone could push at any point, and then you would have some situation that would be completely fucked up, because different people would do different pushes on the same place. Not good. So the way it actually works is that there is one repository called the origin. This is a name out of convention. It doesn't have any meaning. But you can think of this as the, let's say, as the source, as the point where everything branched out from. This is a repository where everyone can read and fork it. What does forking mean? Forking means that you have a remote and you create simply a copy of the remote in your own account. Imagine a situation when this origin repository is owned by me, and you over there, you want to contribute to this origin repository, but of course I will not give you access because I don't trust you. What do? You fork it. You make a copy of this, and you can work on your copy. And you can make your changes on your copy, and I can see your changes, and I see they are good. And now suddenly I trust you. So a fork is just a copy of a remote, of a repository or anything that you can own. It's your it's owned by you. So developers therefore fork this origin repository, and they propose changes by doing what is called a pull request. This is the thing you want to learn in this block, a pull request. A pull request is something simple once you understand it. So here this sketch indicates what's going on. We have the origin over here, and what happens is the developer creates a fork. It could be a fork, it could be directly a branch of the origin if the developer is part of the team that owns the origin, of course, but let's say it's a fork from now. So this is online, remotely. What the developer does is it pulls the remote so that they can work on it locally. So the developer now has a local copy of the remote, of their fork of the remote on their computer. They work on their computer and they use Git exactly like we described so far, with branches and everything. And then they have this branch that they call, feature whatever that I want, that they have developed. And now they push this branch into their own version of the origin, their fork, okay? So now they have finished their development and they pushed it online. Then they can go to GitHub, or actually you can also do it by console, but from the GitHub is the easiest way to do this, and they click make a pull request. GitHub automates this for you very straightforwardly, and it tells you, you have this fork, and now you want to make a pull request into the origin. A pull request does exactly what the name suggests, right? You're requesting this origin, the central repository, to pull your code, your changes into their origin. That is literally a pull request. It is an offer for a code contribution, okay? And that's exactly how things work. Now, once this pull request is opened, there may be people that come around and look at your changes, look at your code, and they say, oh, I noticed that there was a typo there. Or they give suggestions for improvements. They say, oh, I have tested this as well, and I saw that this other method is faster to do this, or whatever. So this is a process that may optionally happen. And once this process is over, the integration manager comes along, which is simply a person that has administration rights for this origin. So they have access rights to this, and they can literally just pull your code in there. And now your code lives in the origin. Now you might think these are many steps and many middlemen going all the way from here, then to here, then to here. But this is really the safest way, and honestly the cleanest way you can do this. So that's how things really work. We will have now examples that you try to do this as well, so don't worry. I will quickly show you one pull request just so that you see how it looks like online when you go to actual GitHub. It really is straightforward. So this was a very nice request. Some person wanted to contribute something called bstub in one repository. And this is what you see when you open the pull request. But of course, most of the time, you're interested in what happens over here, which are the changes in the files that this person wants you to pull into the central code base, right? And you can go through the changes of the files. Green background are files that are being added or lines that are being added. Red background are lines that are being removed, etc., etc. And here you could really, at any point, you can click here and comment on this specific line of code. Say, oh, this is a typo or whatever, okay? You could do this. And there are many other useful tools. And typically, there would be several iterations through this process of you giving some advice to the contributor and the contributor integrating the advice and so on and so forth. And the reason I chose this pull request is because it has a lot of discussion, as you can see, but the overwhelming amount is about the design of this new interface the user wants to contribute. There was very little discussion about performance and bugs, just to highlight that really the design is really important and you want to spend time to get this right. Anyway, something that is not immediately intuitive, but the way pull requests work, they are, and this is becoming clear here, they are from one remote and one specific branch of this remote to another remote and a specific branch of this remote. So this is from the remote kallel-r, which is the username actually, and the branch based in fractions. And the pull request is towards the remote Julia Dynamics, which is the owner of the central repo and the branch master. This means, therefore, that the connection or the pull request is really about the branches, not about the commits that you open the branches at. Therefore, if we go back to this nice sketch I showed, you've received some comments and now you want to integrate them or to use them. Once again, you do exactly the same thing. You go back to your local code, you do the changes, and you push them to your own fork. You do not have to update your pull request or do anything. The update is automatically done because remember, the pull request is about the branch. So therefore, if you update the branch, the pull request itself is also updated magically. Okay. So that's the way it's done. I wanted to give some advice now on pull requests, but I decided I will do it the other way around. We will first do a pull request as an example, and then I will give the advice. So, the exercise for you now is to just make a pull request. Really, as simply as possible, just fork this target first of all, make a GitHub account if you don't have one already. And I strongly recommend you to actually upload a profile picture of you instead of leaving the default one. Then fork this repository and take this. If you fork it, now you have a remote somewhere online. So the first thing you have to do is get the remote locally from the commands I showed in the previous slide. I will upload them again in a moment because I uploaded the wrong slides, sorry. So after you fork it, this happens on GitHub. There is a nice button on the top right that says fork. It's really obvious. You will find it. Then you have a copy of this repository on your GitHub account, remotely, online. So the first step is you take this locally, you pull it locally, or you check out it locally, and now you have it on your computer. Just make these trivial changes that I say here, make a new file, contributors, first name, last name, whatever, that describes you, and then make a bullet point under the section contributors and add your name in a branch. Then you push this local branch of your fork to your version of the remote, and then you go to the GitHub remote, you click make pull request, GitHub takes everything for you. It takes care of everything for you. That's the process. It is really simple once you know how to do this. So now let's see how simple it is when you don't know how to do this. Go. Yo, what's up? This is George from the future again. So 2 quick things. First, please don't do pull requests in the repository that was advertised in the previous slide. As you can see, I have now updated the slide. The link to the repository is not there simply because I'm not the tutor anymore and I will not be looking at the repository and I will not be helping you with your pull request. First part. Second part, I strongly recommend that you use GitKraken. I'm not affiliated with GitKraken. I'm not paid by them. It's just an amazing software that I recommend my students to use. While we were tutoring this course, it was very obvious that people that used GitKraken scrolled through this exercise very, very easily, while people that just used the raw Git had so many difficulties. So GitKraken makes things intuitive. I strongly recommend that you use it. Okay, see you, bye. Okay, team, we continue, vamos. So before we move into the next section, I just want to give a couple of tips for working with pull requests or for doing good pull requests. And if the gods bless you and you get pull requests on your own code, how to actually address them while being a nice person, which is very difficult for me. So I'm happy to share these tips. I try to follow them every day. So the first thing is, we just saw GitHub, and I just told you most of the software you use, if you're a Python user or a Julia user, is on GitHub. Therefore, if you find a bug, the best place to report this is on GitHub. Go to the GitHub page of the package you use and try to report this bug. First, search if there is a report already. And obviously, you would want the developers to fix your bug as soon as possible. How do you achieve that? How do you make a convincing bug report so that the developers are more likely to fix your bug? These are some good tips I could give you by opening a good issue report on GitHub. The first is to try and make a minimal working example. This is a reproducible piece of code with no unnecessary code commands that when it's run, it creates the bug that you have encountered. So try to distill the problem into a minimal piece of code that doesn't have to do anything with your science. It should not use datasets from wherever, NCAR, or I don't know where the hell you get your datasets. It should be something really clean and minimal. This also helps you clarify if you fucked up or there is an actual bug. Then when you have this code, put a clear description of your bug and the behavior you expected the software to have. Provide your environment status, which is the package versions and relevant dependencies. We will discuss how to do this later in the course. Don't worry if you don't know how to do this. Use correct syntax for code formatting with backticks. We will learn in the next block how to do this with Markdown. And try, if you want extra kudos, try to understand and locate the problem by examining the source code, because it is most likely that the packages you use are open source. And simply stating that you appreciate the package, and this makes a huge difference for the developer. I'm much more likely to respond to an issue that says, hey, thanks for your work, but I encountered this, than an issue that says, I encountered this. It's a psychological trick that I'm telling you now how to abuse. What you absolutely should not do is paste links to codes or files or web pages that the developer has to read in order to respond to your issue. That's the best way to make the developer never respond to you. You should summarize the content that is necessary for the answer and simply provide links for further information that may or may not be necessary. And once again, make your code minimal directly in the issue. Don't put a link to your code from your production or whatever that is 500 lines, make it minimal and put it in the issue. Avoid links. All right. Yeah, okay. Now, you learned how to do pull requests or tried to do it in the technical manner. Now let's talk about the social manner. When you open a pull request, you want to contribute something to a software, but you also want to make the work of the people that will review your request easy so that it doesn't take long. And this is also to your own benefit because your request gets merged faster. So some, let's say, tips for this is that your pull request should have a good summary of the proposed changes with human words. So don't just let the developers read your messages or your changes, but provide a couple of sentences of description. If you want to add a new feature, you should also add tests and documentation to this feature. If you try to fix a bug, you should add a new test that captures the bug. If you remember yesterday we were discussing unit tests, these are called the regression tests. When you encounter a bug, you add the test that tests this bug that you fixed. Some repositories have pull requests guidelines. Be sure to read it if there is such a thing. And ensure that tests pass. Don't open pull requests with failing tests. It is very unlikely to get a review in such a request. Another tip is that a pull request is your own creation, and it is likely that you will have feelings of attachment to this, especially if it is a serious contribution that took effort. And especially if it is a serious contribution, it is very likely that review comments will come. Some of these comments may point out mistakes or deficits of your pull request. A good tip here is to lower your defensiveness and welcome these comments. Don't view them as a negative quality of your own self, because they aren't. View them as a chance to improve your pull request, because that's exactly the point these comments are made, to improve your pull request and also your coding skills. Throughout the lifetime of the pull request, try to update the description of the pull request, which is the topmost comment in the PR discussion. And if a pull request is taking too long, don't be sad, mad, or angry for the developers. This is really what it takes for good design. Feel free to regularly ping the developers with reminders like @Datseris, hey, could you please review this pull request? And if I don't do it, then again, hey, do you have some more time now? Just be annoying if you have some kind of meaningful contribution. Now, if the gods bless you and you get meaningful contributions and you are the one that reviews, there are once again things that you can do well to make the person feel better and to make your own life progress faster. The first thing is to depersonalize code ownership, which is, if you think about it, kind of the spirit of open source. It is no longer your code, it is the people's code. So don't think about your own code that someone else tries to fix because your code is bad. Raise the confidence of the pull request author by simply appreciating the contribution and pointing out the positive things first in the summary of the review. Try to use, let's say, inclusive language, which is we instead of you, or in general, third person. Avoid we's and you's altogether to communicate changes. For example, you should reuse X function here. Do instead, we can reuse X function here. Because once again, it is our code. It is the people's code. It's not mine. It's not yours. It's everyone's. If you ask, why did you do it the X way, the Y way is better? A much better way to say this is Y way is better than X way for doing this because of ref Z, which is some kind of a much more objective statement than an attacking statement. Oh, your way sucks, man, get it together. So, however, you also should be clear, because clear communication is the most important thing. If your expertise clearly deems something that is wrong and needs to clearly change, you have to say this clearly as well. So don't be overly polite simply for the sake of being polite. Don't say, maybe this part isn't the best because it does this thing and some people don't like this thing. I wonder, maybe can we do it differently? So for example, some people do X. This is an overly polite statement full of unclear things. The correct way to say this is, these lines commit type piracy and hence cannot be merged. Change them by doing X. That's it. That's the end of the story. It's an objective statement, and remember, you already said the positive things at the start of your pull request. So the person is primed to welcome changes as a positive improvement. Okay, so that is about, let's say, the social aspects of pull requests. Now we go into something ultra uber cool that GitHub and pretty much every other service has, which is called continuous integration. Continuous integration means that loosely speaking, your test suite is run automatically by an online service. And typically, this is really simple to set up. At least for Python and Julia packages, it's very simple. And it's completely free as well. And this CI, as it's called, it's triggered every time you push a new commit to your repository. This is also true for branches most of the time. And this is also true for pull requests. So when you open the pull request, actually let's show this, this is nice. Because you were the first time contributor, I have to approve it manually, but if you have contributed before, I don't have to approve manually. Now I approved the pull request to run, and now you see this thing opens up over here that runs the test. So I can click the details, and we will see all the things that will happen here. And what will happen here, I will just tell you so we don't have to wait, is this, let's say, process will install Julia, it will install the packages necessary for this repository to work, and then it will run the test suite of this repository. Okay, so this is really nice if you think about it, because it is automated, and therefore it really gives you confidence that things do not break over time, provided that you only merge things that pass tests, of course, right? And on the next block, we will also see that we can use this exact same process to also automatically generate documentation or host documentation for our project. So let's go back one more time and see what's going on over here. Was there a question? Oh, okay. All right. Great. So that's continuous integration. We will see how to set it up now. If you're using GitHub, the way this is done is via GitHub Actions. So in the repository you forked in the previous exercise, there is this special file in the folder .github/workflows/ci.yaml. Please open this file on your computers. Remember that some operating systems might hide folders and files that start with .dot by default. Just go to your system settings and change this. So let's go over this file and see how it works, how it looks. I will also show you the Python file, don't worry. Where are we? Yeah. Code, GitHub workflows, file. Okay, this is a really simple file. Here we declare where this should happen, where this file, this workflow file should be triggered. And it is on pushes on the branch main and on pull requests everywhere because I don't specify. So in all pull requests and any push on the branch main, what follows will be triggered. There is something that we don't care about. It's about canceling jobs, so we don't do twice the same thing, but let's not care about this. Now this is the main bulk of the work, where we start and we first specify the version of the language we want to use. In my case, this is Julia. We specify the operating system we want to run our tests at, and this could be several of them. And then we define or we include the steps of the running the tests. Now, for most programming languages, there are already pre-existing actions that GitHub has stored that start the process. For example, there is an automated action for setting up Julia over here. That's how it's called. It's literally called Julia Actions Set Up Julia. There is an action for caching installed things so that we don't have to re-download everything all the time. And there is an action that builds the packages that my project needs to run. And then the last thing that I do is this command over here that I named it run tests. This is the final step, let's say, that literally runs this. It literally calls Julia and runs the file test.runtest.tail. That's it. It is really that simple. Of course, here you could type anything you want. It could do anything. But for me, it just tests my repository. And the Python version is github.com. Example Python. Is it example/Python? Yes, yes it is. So here it is very, very similar. Once again, you see we have the same exact, well, not the same exact, but you see that once again we have these predefined commands for Python here for the conda package manager that sets up this mini conda installation. Here we have the steps that activate the environment we want to use. This tells the CI what packages we need, of course. And then we create a new command that installs packages. This is exactly what this does. It installs all packages necessary. Well, dot is current directory. And then we test. Python has this pytest command line command that runs the test of a folder. So it automatically detects where the tests are and runs them. And of course, once again, dot is just current directory. And the documentation, we will not see it. But I hope it's clear to you that this is a really straightforward thing. And the most important part for you is you can just copy paste this. You see, nothing here depends on my name or on my repository. Just copy this, paste it into your own repository, boom. Magically, you have continuous integration enabled. Really cool stuff, no? Okay, where are the slides? Yeah. Okay, so now you're very close to putting your code on GitHub. Very, very close. But we have to talk about licensing. Something that is on GitHub and does not have a license is, by default, untouchable according to GitHub. All rights to the source code are reserved by the owner, and no one may reproduce, distribute, or create derivative works from your work. So this, if you think about it, kind of defeats the whole purpose of open source. So put a license there. Which license to choose? Well, you can use this very, very good website if you need further advice. My personal recommendation would be to just use the MIT license. This is the most permissive license you can have. It allows people to do absolutely anything with your code, to make money, to completely alter it, to distribute it as their own. And it gives no warranty or reliability claims, so it gives no burden to you. So this is really the most permissive thing. It is used by approximately half of GitHub, which is amazing if you think about it, because there are maybe 20, let's say, valid licenses that people use. So it is clearly and by far the most popular. The entire Julia programming language and every single package I know about this language just use this license as well. Okay. So now we go into the part of the exercise that is already for your own code. And as you can see, we have a lot of time to finish this thing. So if you haven't really dialed in pull requests, go back to the previous exercise and continue working on this aspect, because now the recommendation here is to put your own code on GitHub. Now, many, let's say, beginners are scared to do this because some people have the worry that other people will steal your science if you put your science and make it public. My tips here is to first remember that science is about openness and acknowledging other people's work. So it is the duty of other scientists to not do this. But also consider the fact that, is it really possible that someone that knows nothing about your work can really publish it faster than you? That sounds to me really impossible. Anyways, if you really are scared about these things, just make a private repository. GitHub has the option that you can make either a private repository or a public one. Make it private if you're scared about these things. I'm not scared about these things. I also have to mention here that there are other hosting services that exist. The second most common one is GitLab. In comparison to GitHub, GitLab is not owned by Microsoft. Yes, GitHub is owned by Microsoft. GitLab can be self-hosted, and continuous integration in GitLab is really hackable in the sense that it can even access your own computing resources or your own cluster or your Levante or however it's called. On the other hand, GitHub has much better community support, and it is much more well-known and it's much more accessible. Therefore, it is much more likely that people will see your code if you put it on GitHub. And that is my primary purpose for putting my code online. I want other people to use it. And therefore, for me, GitHub is a better choice for that. All right. So once you create a repository on GitHub, you can add continuous integration by following the slide on continuous integration, which means just take the files. If you're a Python user, take the Python file. If you're a Julia user, take the Julia file. And add the files for continuous integration by making a local branch, once again, called CI or whatever, adding the files, pushing the branch to the remote, and then making a pull request from the branch to the main branch. Oh, that's something I didn't make clear in the presentation. Pull requests are also done within your own repo. You don't have to do a pull request from one remote to the other. You can do a pull request from the same branch, from the same remote, but a different branch to another branch. So you can still practice doing pull requests now with your very own repository. You don't need my anymore. So anyway, do a pull request from the CI branch to the main branch that adds these files for continuous integration. And if you do this properly, you will see that during this pull request, continuous integration will run for your own repository because the pull request will have the files for continuous integration. So once you have done all these things, add another tag to your code base and this time call it online. So remember, this is an exercise you do in the existing Git repository you have started for your own code base that we started yesterday. Remember how we add remotes? We add remotes with a push, git push command and the track command. No, wait, sorry, the checkout command and the tracking, sorry. It's in the slides. So if I said something wrong, the slides is correct. And we have a lot of time for this, so me and Lucas and hopefully someone else will really try to help you to set this up, okay? The next exercise would be that you do a pull, you take a collaboration partner or whatever, and you do a pull request to your collaborations partner repository, and they do one to you. Okay, this block is very dear to me. It's something I like a lot and I appreciate a lot. And I think it's much, much more important than people think. It is about documentation, and not just documentation, but good quality documentation that conveys information efficiently and intuitively. Let's start with a nice meme first. So this is a person that has not read the documentation of the teapot and believes that this is how teapots work. And also claims that they do not need, sorry? Yeah, exactly. Well, if you can make something work, it does not necessarily mean you made it work with the best way possible, but of course you need documentation in the first place. So if teapots didn't have documentation, maybe that's how we would use them at the moment. So why would you bother with documenting your code? And the main reason is because you want people to use your code. It benefits other people and your own self if other people use your code. But of course, if people can't figure out what is the purpose of your code, how to install your code, and how to use your code, they will not use your code. This should sound obvious to everyone because it is obvious. Furthermore, learning a software by its source code is tremendously inefficient. I like this quote so much. There is a vanishingly small, like, this is such a nice word, right? There is a vanishingly small amount of people who will source dive to learn any code out there compared to the amount of people that would use the code when it's properly documented. This code comes from a very big figure in documenting. It's the co-founder of the Read the Docs infrastructure that actually our default project template uses for Python. And in fact, we would add that for a really complicated software, it is literally impossible to learn it from the source code alone. You cannot learn it without documentation or without someone just holding your hand throughout the entire of the process. But we are strong, independent people, and we don't want anyone to hold our hands. So the third reason you want good documentation is because it will likely motivate contributions. You can only get contributions after having users, which only comes after having a documentation. So there are many very, very good reasons why you want to document your code. So, according to my opinion, documentation is by far the most important part of a software. That is my opinion on documentation. Now here is another very nice meme. You get a tech job, you ask for the documentation for an internal project, they tell you there is no documentation, just look at the code. I mean, how hard can it be? The code has no comments, the variable names are 3-letter long acronyms, okay, in our case it's 4, it's so much better, and most files are 2,000 lines of code. I would also even add legacy code. Does this sound familiar? Well, let's see how we can make this better. So first, let's reflect. What is the role of documentation? Well, first, it teaches new users how to use the software. That is the primary goal, I would say, even of documentation. Then it serves as a reference for existing users. And the third goal is the documentation defines the public API. Remember, API is literally what are the functions I use to use the software. Therefore, it is the documentation that defines whether something is a bug or not. Many people don't know this, but that's actually how it works. Because remember, only the intended behavior of a software can be described, not the actual behavior. That is simply too complicated. So it is the docs that define what is a bug or not. Therefore, here we can now formulate what should be good documentation. A good documentation will make the user understand what the software is about, get an immediate overview of what the features of the software are, find the information they need fast, find it where they expect it to be, understand the information quickly, and have no ambiguity after reading the docs. So you see here, a good documentation have many more attributes than just listing whatever the hell you can do. It is also about efficiency and the intuition. A good documentation should be intuitive. You shouldn't have to spend years, okay, maybe days, finding out where things are. Now, before we go into the next slides, which are about structuring such documentation, I want to give a quick comment. This is my own opinion, of course, but especially in today's age where Googling is the first thing we do, that's a bit important. I would recommend, instead of Googling when you want to solve a problem, to instead read the documentation. And the reason I recommend this is because just getting a quick answer to your problem from Stack Overflow solves your problem but doesn't actually teach you something. Learning the documentation improves yourself. It teaches you how you can answer your questions. So my recommendation is first read the documentation before Googling to try to solve your question about a specific software, of course. Okay. Now we are starting to learn how we actually write documentation, and my recommendation and how I do this is something very, very simple. It's called Markdown. And Markdown is simply a way of writing plain text files in a way that they can be, let's say, prettified or rendered to something more complicated later down the line. And the Markdown syntax is exceptionally simple. You start, hashtags are making headers, and nested or many hashtags in a row make headers with subheaders or sub-levels of headers. So this would be the highest possible header. This would be the title, let's say, in LaTeX. 2 hashtags would be section in LaTeX. 3 hashtags should be or would be subsection in LaTeX, and so on and so forth. That's one of the syntaxes Markdown provides. The other thing is that it can do lists, like the list that you see here. List starts with a dash. It can make some text bold by adding 2 asterisks before and 2 asterisks after the text. It can make text italic by adding underscores before and after the text. It can do links by enclosing some piece of text in brackets and then adding a parenthesis and the link you actually want. It can even do math, but the math depends on the renderer you will use, so I will not cover it now. The example I will provide does have math anyway. Markdown can also do numbered lists like the one you read now. Fun fact, the actual numbering I use doesn't matter. I could make all of these 1, and once rendered they will actually be 1, 2, 3. Markdown can do tables, can do inline code. So if you have a piece of text that is enclosed into backticks, these ones, it will be rendered as code once you render the Markdown. It can do code blocks, like the example I have here. This is a Julia highlighted code block that has 3 backticks, then the word Julia, which is the language to use highlighting for, and then 3 backticks again. And I have a link here to the Markdown guide that has much more syntax guidance if you need more, but in my case, at least, these are the things I use 99.9% of the time. All right, so where do we use Markdown? We use Markdown in documentation strings. Documentation strings are descriptions of what a function does, how it can be used, and documentation strings form the basis of a scientific software documentation. Documentation strings are written in human language using Markdown or other simple alternatives to Markdown, but simple syntax, that's the point. But documentation strings are not comments, okay? They are superior to comments and should be preferred for explaining things whenever possible. One of the many reasons they are superior to comments is because they are accessible from within the language interactively. So if I pop up my Julia, and I wait for it to start, of course, and if I go into help mode, Python also has a help mode, and I type cosine, what it will pop up for me is the documentation string of the cosine function. It's not comment I added into the cosine function in the source code. It is the proper documentation string. Okay? So that is what I mean they are accessible within the language interactively. And in my opinion, the public API, so how users should use the software, should be defined entirely with the documentation of exported names. So let's say you have 6 functions, and 2 of these functions are expected for public use for other users, and the other functions are internal that are called by the functions that should be used. Well, the functions that should be used have these documentation strings and the names that I choose to export. Depending on your language, there are ways you can explicitly say to the language, I export these names. Maybe there are no explicit ways. In Julia, there is an explicit way to do this. What I do, and what I recommend you to do as well, is to first write the documentation string and then write the function. So imagine what it should do. This is exactly the same tip as what I gave you in block 3 about software developer paradigms. You first put the hat of the user and you think about what I want to be able to use. So you write this down. This is exactly the documentation string. It tells you what it does and therefore how you can use it. And after I'm done with the documentation string, I write the source code for the function. Okay, here is an example of a documentation string. Click. The internet site reports cannot be found. Okay, I'll have to do it the hard way, unfortunately. Sorry, I messed up the link. We go the hard way. I will update the correct link, of course, in the thingy. Very nice. Source use, maybe, yeah. Okay, so Lyapunov exponent. Let's find this bad boy. Yeah, sorry, this should have been instant. My mistake. Maximum. Okay, so this is how a documentation string is rendered once you go and generate your documentation. So what you see over here is the documentation string for this function called Lyapunov. This is a code block. You see this is rendered as code because it uses monotype font. And then there is the actual description. It says calculate the maximum Lyapunov exponent. This is also code because it has this purple background and it's monotype font. Using a method due to Benettin, which simply does whatever. See also this and that. Then there is a list of keyword arguments over here. U0, the initial condition, etc., some other things. Then there is some description. 2 neighboring trajectories do something, whatever. There is a mathematical formula over here. There is another section that says performer nodes. And let me go back to the top. Sorry. My mouse is terrible. And I could click this thing. This is a hyperlink. Actually, it brings me to the bottom and it is a reference. So that's how it looks like in the actual documentation. And now this is how it looks like in the source code. Lyapunov. Okay, this is how it looks like in the source code. It's from here all the way to here. So another markdown syntax that I didn't mention is that if you ident text with 4 spaces, it automatically becomes code. But anyway, this is the documentation string. It starts with something that is rendered as code. Then it has standard text. Remember, things that you put in backtick are code or are rendered as code later. This is how you make references. This depends on the renderer. For the renderer I use, this is how you make references. If you use Python, it might be different. I'm not sure. This is now a subheader over here that says keyword arguments. You see we have this bullet point lists over here. There is another section over here with description. In my renderer, the way I type mathematical formulas is with having 3 backticks and then math. In your renderer, if you use Python, it might be slightly different, but don't worry, this is in the example repository. And whatever, there are some other things. Here is how, in my renderer, this is how I can reference other functions. So with this syntax, I can reference other functions which have a documentation string. So this is if you want to cross-link, which is super useful, by the way. So if I go back, I can click this, and it will bring me to the Lyapunov spectrum function. Or I can click this and it will bring me to another function. So that's how it works on paper. Okay? Of course, you will have to get familiar with the syntax and practice it a bit. And this is what the next exercise is for, so don't worry, we have exercises for this. Now, here is how I suggest to create your documentation strings, because this is how I believe makes the best documentation strings. This is my opinion. But my users are very happy, so at least I'm not the only person that believes this. So, the very first thing you must have is the clear call signature in actual code syntax, including expected input types if necessary. So if we go back now here to the previous function over here, this is actual code syntax, and now I'm using my language's syntax to annotate the expected type. So it becomes clear to the user that this has to be a subtype of dynamical system. And therefore, this is not information I have to repeat in the documentation string, because it's already clear by code. After that, you should have a brief summary of the function. That's exactly what this piece over here does. It's a very brief summary of the function. After that, then all the remaining depends on context. You should have the return value type if this is not obvious from context. For this specific function, this is obvious, so I do not discuss it. It returns the Lyapunov exponent, which people know is a number. Then references to related functions if sensible. For this function, this is sensible, and there are some references to related functions. Then a list of keyword arguments if the function has keyword arguments. That's exactly what we have over here. Then optional, detailed discussion of the functionality if the function behavior is scientifically involved. This is something I always do and I strongly recommend. This is a function that is scientifically involved. So I describe in a couple of paragraphs the algorithm that actually does the function. And then if this is not enough, we go to the very final point, which is citations to the relevant scientific papers, which is once again what we had at the start. This is the paper I got the algorithm from. So that's my recommendation on how to make a really good documentation string. Always strongly recommend to have a clear distinction between code and human language by using these backticks that, as I said, format things as code. When you are referring something that is in the call signature of the function, so if I was referring to this thing over here, if I was referring to Lyapunov, it is much better to use the actual code Lyapunov in backticks. Okay. Yes, examples are extremely useful, but I actually don't use examples in documentation strings. I use examples in runnable code, which I will show you in a moment how to do this. But first, let's try to get a bit familiarized with documentation strings. Here I'm saying you can get the running means function. So this is the code I wrote in block 3 for calculating temporal means. Sorry, do I say running means here? It's temporal means, not running means. But of course, there is also the version of the code with the running means that is for Python. The Python version was already documented, so now I replaced it with an undocumented version. Of course, if you have downloaded the previous version, you have the doc strings already, so pretend they are not there and delete them. But I also recommend you to try to do this in the Julia functions, because this doesn't matter about code, it's about documenting code, which is human language, right? So you don't really need to know the programming language. So spend, let's say, 15 minutes trying to write documentation strings for either the running mean codes or the temporal means codes. Go ahead. All right, we had enough time. I'll show how I approach this exercise. So how I wrote the doc strings. I had a discussion there. You can I don't know. I still recommend even in Python to consider this system, because in my opinion, this is my opinion, of course, right? It is more important for me to have a high-level description of the function as the first thing, and then later get all the options the function has, than to get all the options the function has at the beginning, and then have to scroll 200 lines to get the summary in human language of what the function does. So I would much rather, the first thing that I read now is calculate the maximum Lyapunov exponent. I think this is more important information than the information that this function has a keyword delta t. So this is why I would still recommend to consider a handwritten call signature. That's my opinion, as I said. I repeat, my opinion, but I found it helpful. So, how I approach these documentation strings? Well, there is this function monthly minutes that I think is the simplest one to document. It has this call signature. It takes t and x and returns w and y and says given a time vector t and x, some values corresponding to it, average x over months and return w, the new monthly now spaced time vector, and y the monthly average x. See also month ag. So month ag now is a different function that has an extra keyword argument ag at the top and says given the time, actually it says exactly the same things, but the only thing it does, it says aggregation is done via ag, which maps a vector of values to a number. So of course, if this function ag is the min function, then this function does monthly mins. And now the function that perhaps is the hardest to document is the temporal aggregation function. And as you see here, I make the choice to describe the types of the inputs in the function call signature itself, rather than text. Either way you do it is fine, as long as you do it if it's necessary for clarity. And it says calculate the temporally aggregated version of x, where it has been aggregated over periods of time dictated by the info function. Return wy with y the aggregate. Okay, this is the same as before. Now this is something new. Info decides the intervals used for aggregation. All sequential values of x that have the same info belong to the same interval and are aggregated using ag. Typical values of info are dates year, dates month, dates day, and etc. You could define summer x equals month x inside this and use info equals summer to find ranges that correspond to successive summers, whatever. And there are some other info, and again, referencing. So that's how I would approach it. All right. Don't worry, you will have plenty of time to write documentation strings for plenty more functions. So now we go from documentation strings to documentation pages. So after you have the documentation string, you can make them into a full documentation for your own code base that can be hosted online. But then you ask, what should be in your documentation? And my first approach would be it's as easy as 1 to 3. One is the home page, which is the first thing a user will see when they enter your documentation. The second thing is the API declarations, which is literally exposing the functions the user can use to use your software. And this means literally just taking the documentation strings that you have written and rendering it from Markdown to an HTML. And of course, using connecting sentences where necessary, right? If you just dump some documentation strings, that may not be clear itself. And the last thing is to have some kind of tutorials or examples that have an educative usage of the code base. These, for example, could be Jupyter notebooks, but everything above should not be Jupyter notebook. Okay, so let's start with the homepage. What should you include in this homepage? Well, if you can, the first thing, the very first thing at the very top or at the very side should be a logo. It makes your software unique and memorable, and it shows that you care enough for it to give it a face. This is one of these psychological tricks where a user will instantaneously believe that the software is better because it has a logo. This is true. Then you have an introductory paragraph, which must capture in only a couple of sentences what this software is about. Then, preferably, you have, if not obvious, of course, you have a getting started section that says how to install the software, if there is any preliminary knowledge required, and how to navigate the documentation if the documentation tends to have a lot of pages. Then you could have a list of features of your software, and if this is too expensive, extensive, you can make it a page, just a small bullet point list that tells you that's the things you can do with this software. Or a large bullet point list if it's a large software, of course. And then optionally, you can describe how you approach the software from your design, which is probably useful for people that actually want to see their source code and perhaps contribute. Yeah, and the last thing is how to ask questions or how to get involved in development if this is something you care about. You don't have to care about this, of course. Okay, and now we go into something really important, for me extremely important, which is depth of exposition. A good documentation has various levels of depth of exposition. The highest level is literally the summary of what the software does in a couple of sentences. This is the very first paragraph in your documentation. The high level is one overarching tutorial on the core or the main bulk of the software that takes the user from the start and walks them through a full, let's say, workflow that uses this software. Then the intermediate level would be examples that showcase end-to-end usage of specific functionality or advanced functionality. And then, and now that I said examples, but let me show the lowest level. And then the lowest level should simply be the declaration of the public API, which literally means just put the documentation string there. I have a comment here, and I strongly stand about this comment. Examples must be run, not written. This tremendously lowers the risk of broken or unupdated doc pages, because with this continuous integration, you also get messages of error for the documentation, not only for the tests. We will see an example in a moment. And I will not explain exactly how to do this. Each language has tooling systems to achieve this. I will mention some in later slides. But we will see now what I mean by this. So one example for documentation that has been celebrated many times from other people is this software called Agents. So what I want to highlight here is the structure of the index page. This is the name of the home page. The tutorial page, the API declaration and the relation to the sidebar, and these examples are run, not written, which you will see now it makes sense. So this is, oh, no. So this is the documentation page. It starts with just one sentence that says this is a framework for agent-based modeling. It has some nice new stuff for the returning users. Then it has this features paragraph over here. It has installation instructions, which honestly are not necessary if I am to say, some design philosophy and whatever. And then there is this section, which you might want to consider also on your own, which is for people that don't know what this is, that don't know what agent-based modeling is, but maybe want to learn. So this is our, let's say, our view or our summary of what we think this is. This you might think is not necessary, but sometimes it's nice because sometimes people come along and they think they are not sure whether they need this or not, and this makes it really clear for them. Then there is this dedicated tutorial page whose only purpose is to just take a user that has not used this software ever before and walk them through these 5 or 6 steps that are necessary to get this working starting from absolute zero. Of course, I will not go through because you don't care to learn this. Then this is the API declaration. This is a page whose purpose is literally to expand all the documentation strings of the library. That's exactly what this does. It's just expanding documentation strings and puts small connecting sentences where necessary. And what I want you to pay attention is the sidebar. So the sidebar is this summary, let's say, of the contents or of the headers that exist in the documentation at the highest level. So these are the highest level headers. And then these headers over here are the headers of the current documentation page that I'm viewing. And it is these headers that are very important because it is these headers that will guide the user to what they want efficiently. Remember, good documentation is not just good information, it's also finding it fast. And that's very important for finding fast. Of course, there is also a search bar, but if you can read it, it's simpler than searching it. Sometimes you just search it and you find it, sometimes you read it and you find it. I will just go into one of the examples of this, and I will show you what I mean by this is run, it's not written. So I will go to edit this. So the way these examples are created, and in Conrad the same thing happens with the plots in Conrad, is this video you saw, I have not created this video, saved this video somewhere, and then put a link in the docs. No, this video is, well, what the hell? This video is created while the documentation is generated. So what it happens is it takes this standard Julia file, this normal runnable piece of Julia code, and you see this piece of code is annotated with some comments in the comments themselves use markdown syntax. Okay, this is a bit meta level, but the comments themselves use markdown syntax. What my documentation generator is doing then is taking all the parts that are not comments, and it knows this is code I have to run. So what happens is this code that you see over here, it creates a video file, and at the end, when I have the video file created, so I have a video file that is created, and then I have these pieces of comment over here. Remember, these comments will actually become HTML syntax when my generator is through them. And what these comments actually do is, well, first I have some pieces of code over here that create a video. Where is it? Let me make it clear. So this is just some function that actually makes a video. So I have not created any video myself, the code does this. And then I have this piece of comment that the only thing it does, it just displays this video. So this is what I mean by examples must be run and not written. I have written code that does the example. I have not written the example. So every output of the example, that's actually what I should say. The output of examples must be run and not written. So everything that you see here that is output of the piece of code, I didn't write it. This is just what the code outputs. And that's how I would recommend you to do it if you reach this advanced level of having large enough documentation that needs examples. I strongly recommend that the examples are run, not written. That's what I mean by run, not written. So when we go down to the video point or the plotting point, I have not saved this image somewhere in a website that I link here. This is just the image that this piece of code generates. Now I want to return to this because I think the table of contents is very important. And here I have a term, like a catchphrase that you might help you remember this, the eye horizon, I call it. So what happens when you have a documentation page in front of you is you will scan its contents. You will scan the contents of this page as you land into this page, and you will have this thing. So this is, you will scan this immediately, and based on this first initial scan, you will try to guide your brain on where is the next thing I have to click to go. So here you would either click the scroll thingy, or you would already see the sidebar and you will scroll this sidebar. For me, scrolling and clicking is the same thing, okay? And I see, okay, I was here just because I wanted to move some agents or whatever, and you see this, there is a section that has conveniently this name, so I click there. So for me, the table of contents is the best way to satisfy this eye of horizon problem, which means that the user really wants to have in front of them what they need to click on to go to where they need to go. And a good table of contents makes this as seamless as possible, which means you should get the ordering right. Remember, table of contents is just different headers with different ordering levels. So here are some tips that might be obvious for some maybe not. Subheaders must really be subtopics of the upper level. So a subsection must really contain content that is really a subtopic of the highest level. Otherwise it gets confusing. Same level of information variety must be on the same header level. So when you add section in LaTeX and then you add another section in LaTeX, these two things should have the same level of information. And of course, this is difficult, right? This is a difficult task because you have to have a sweet spot balance between having a good overview, but also don't have an information overexposure. So if I go all the way to 6th level headers and I put a header for every single function name, then the table of contents starts to become useless because it has too much content to be useful. And the last thing I want to say about the table of content information is that it has to be in the same place. All table of content information should really be in the same place. If you're using a layout where the table of contents is split left, right, and top, which is what I did in the past, consider changing that. So here is an example from a discussion of how we improved the documentation of one of the software organizations. So this is how it looked originally, and you see here the table of contents kind of information is split over 3 different things. You have on the top, you have the topmost level of splitting. Then on the left, you have the second level of splitting. And now on the right, you have the 3rd level of splitting. So this is both confusing and unnecessary, and also does not convey which one is the level of splitting that happens. So I know beforehand that here is the lowest level splitting and here is the middle level splitting. You probably wouldn't know this beforehand. So it is much better to have a version like this, where now the 3 levels of splitting really do become crystal clear and they are all on the same place. This is clearly the highest level of information splitting. This is the 2nd level of information splitting, and this black background is clearly the 3rd level of information splitting. So proximity is good for finding information fast. You want things to be close. All right. And the next tip for good docs is that, okay, surely you want to eliminate chances of forgetting to update something. It is really sad if you did some good work and you pushed this work online, but suddenly something was not updated and you forgot about it, and then the user is using something old even though the new exists. Okay, here are 2 good rules of thumb to not eliminate it completely, but try to minimize this. The first thing is, and this is something I strongly stand by, is that documentation must only exist at one place. Only one place. Possible places are GitHub web page hosting, READMEs, GitHub wikis, private web pages, GitLab pages, Redmines, whatever. It's much, much better to have it at one place coherently that also allows cross-referencing things automatically. Personally, I am against having documentation both in the README and hosted somewhere online. I do not agree with this. Many people disagree with me, and I agree with this. You decide for your own self. I prefer in the README to just have this opening paragraph, this couple of sentences about the software and absolutely nothing else. And here a quick clarification. Notice, for small projects, often it is not worth it for you to make a documentation, and the README by itself can serve as the entire documentation. That's totally fine. That's not what I'm talking about. I'm talking about projects that are worthy to have a documentation because of their content extent. Okay, the second rule of thumb is that thing X must be defined only once, at one place, and explained at that place in your documentation with as much detail as necessary. All other parts of documentation that use X must simply cross-reference its definition. So if you have a function, and this function uses this class that you have created, you should not say in this function what this class does. You should just point to the documentation string of the class. You should not repeat this information. And so avoid duplicating information. And remember, you can cross-reference using your documentation generator software, so it is possible to just have hyperlinks that just jump from functions to functions. It's not a big deal for the user to just go from your function to this class you have created. Right, that's another nice meme that I like a lot. I really liked this episode, so I love this meme. Okay. All right. One more slide of advice, and then we go into practical things. Use unique identifiers, something that is also known as pick one word per concept. This means that when you are referring to the same things, use the same words. And I mean exactly the same words. And this is actually good advice for any form of technical writing, whether it is a paper or a documentation or whatever. And therefore the same advice also applies to your source code. This establishes an unambiguous connection between the English words and the object they refer to, which is typically an object existing in code. And it is much more important for a technical document to be clear and precise than to be poetic. You're not writing a novel, you're writing a documentation. You don't want to use 5 words for one thing because the user will be bored if you don't use different words. No. For example, you use all these words: fetch, retrieve, get, obtain. Pick one of these words and use it throughout. You use sketch, diagram, concept, idea to refer this one thing that you use in the start of your documentation. Pick one word and use it all the time. All right. Okay, so how do you actually do this? That's nice advice at all, but how do you actually put it in practice? Well, of course, each language has some packages or some software that help with creating documentation. They expand the documentation strings from Markdown into HTML or whatever you choose. They allow you easily to cross-reference documentation strings of one function to the other, etc., etc. They can make HTML pages out of Markdown documents for you. And they also allow additional Markdown decorators, for example, for enabling math or for running code. So you can literally produce your own plots while the documentation is generated, which is the best way to do this. Then you can use GitHub and its continuous integration to create and then host the documentation. And the Julia recommended tool to do this is a package called documenter.jl. The Python recommended tool to do this is called Sphinx. Here are the links for them. It's beyond the timetable of this workshop to teach you these tools in detail. So what we will do now, we'll simply go through the template project that we have online that you guys could download and have downloaded and show you how it's done. So let me go here and show you how it's done, or not, that's not correct. I will not show you how it's done. I will show you how it has already been done. You have to learn how to do it with time and effort, of course. So first of all, let's see the build. This is the build documentation. This is the documentation that was built automatically while the tests were run, and this is how it looks like in the end of the day. It has some nice headers over here. This is the documentation string of a function, whatever. It's exactly like the previous documentation. Sorry, the previous documentation I showed you. It really isn't something fundamentally different. Now, we can see where this documentation comes from. If we go to the docs folder, this is the folder that contains documentation. And then we go into the source folder. Now, the way the Julia tool works is you write markdown files that are later brought into documentation files. So if I click here the row, this is how the documentation looks like as a raw markdown file. So you see, this is normal markdown syntax. I have this first header, first level header, that is the topmost header. And I say here, this is the mandatory index.md file, that is the home page of the documentation. For the software I use, it is mandatory that you have an index.md file. Here is the documentation string of a function. This is how my Julia package takes the documentation strings of the function and expands them into the actual web page that is generated. I will also show you the Python version, don't worry. This is how I can link different subsections in my documentation. I literally take the name of the section, put it in brackets, and then I use this parenthesis @ref. And this is how I link documentation strings. I put the name of the function, but I put it in quotes, again in brackets, and then again at the end I have the ref. Okay, so this will create a link that points me from here to here. Of course, the second thing could be at any page, anywhere in the planet or wherever. Yes? Sorry? @ref. @ref is a special syntax that my tool for building documentation provides. The same thing with this thing. This is a special syntax that this tool that I mentioned, this Julia tool called Documenter, where is it previous? This Documenter tool provides. So this is special syntax that this tool provides. You will see Python also has these syntaxes. They just look slightly different, but the gist of the story is pretty much the same. And so this is where I define my documentation. And then there is a simple file that makes the documentation. And this file is again in this docs folder, and it's called make.jl. And this is a file that I will not go through in high detail, but it uses this Julia package I mentioned called Documenter. And there is one function that builds the documentation. So this function reads all these markdown files I have created and makes them into HTML files. And then there is another function that deploys the documentation. So it takes all these HTMLs that you could now see yourself in your local computer, but puts them on GitHub. So GitHub can host the documentation for you. I don't expect you to understand fully how this works because I'm only giving you the overview, the idea, okay? I don't expect you to know exactly how it works now that I'm closing this, just to be clear. I'm just showing you the basic way it works. Let's have quickly a look at the Python version, which actually already has the instructions in the README of the file. So there are some instructions here in the README on the file on how you build the documentation. So first, you can create the documentation yourself. If you remember in the Julia version, this is what the make docs function does. In Python, it's not make docs, it's make once you are in the doc directory. So it's approximately the same, not identical, but approximately the same. And so let's see this over here. Where is it? Docs. So docs here in the source, once again, is the definition of the documentation. So this syntax is not exactly Markdown. It's similar to Markdown. It's called restructured text syntax. But as you will see, if I go into the row, it's something very similar. So there are some special decorators that the tool we use provides. So this is a special decorator that comes from Sphinx. Correct, Lucas? Yes? So you see, it's not exactly the same as Julia, but the principles are pretty much the same as I can see. There is some special decorator that you can use to reference some things. So here we are referencing the function gen_index. And there are some other decorators that configure, let's say, the table of contents tree. In Julia, this was happening in this make docs function. So everything is very similar. It's just the syntax that is slightly different. Okay. Functions RST, I don't know what this is. Oh, okay, I know what this is. And when we go into the build version, I do not know where is the build version. Okay, so this is where the build version is, and you see, well, what you would expect to see once you learn this special syntax that Sphinx uses. Of course, you have to know the syntax, right? Guys, I'm I'm not going to lie to you. This isn't magic. It's computers. But that's how it works, pretty much. Now, we have set these repositories that they build documentation automatically. The same happens for the Julia repository and the Python repository. So if you clone these repositories and you have your fork, and the fork works, you should have a documentation. For example, if you have cloned this repository, actually, let's test this right now. Let's take a pull request for someone that cloned this repository. So we go here, we click here, we go to their repository. So this is their repository. Yeah, this will not work for them. But I will not explain you now exactly why. It's a bit too advanced. So don't worry about this. But if you were the owner, it would work, I promise. I absolutely promise it would work if you were the owner. Okay, now the rest of the time is supposed to be dedicated on you working on documenting your own code. And of course, the place that we start is by creating documentation strings for our functions, right? This is the bulk of the work. I absolutely promise you, I know it's hard to believe, I promise you that if you do this automated hosting thingy once, it's very, very easy. So the bulk of documenting is really creating the documentation strings. That's the hard thing, I promise you. Once you do this weird hosting thingy once, you know it forever. It's really straightforward. It's just that you have to do it once. So now focus on documenting your code, do your doc strings, think about how you want to explain this, and then do the markdown documents that serve as the documentation. So these documents over here, that they can be marked down or restructured text, you decide. Like, start creating the home page of your documentation, so to speak, and don't worry now how to host it. Once you have everything ready, you can start working into hosting this, which means going at the default repositories we have created and looking at it, and we are here to guide you through. But remember, the by far most important task is to document documentation strings and creating these documentation pages, like the outline of your documentation. Okay? Vamos. All right. Welcome to this final blog. Thanks a lot for persevering. I really admire it and I appreciate it. So the last blog is about something that I think is very important, but unfortunately not other people think the same. So let's hope I can convince other people otherwise. So the blog is about scientific project reproducibility. So let's look at some numbers, so to speak. There was a poll, let's say, yes, poll done by Nature some time ago that asked people, scientists, is there a reproducibility crisis? Unsurprisingly, about 90% of the participants said yes in some way or another. And then there was further questioning on what people think makes a science irreproducible. And of course, there are many, many things here. But we can only address one of the things, which is that the code or the methods were unavailable. Now, I want to say something that you might not believe it at start, but I truly think that reproducibility is like brushing your teeth. Once you learn it, it becomes a habit, and you kind of automatically write projects that are reproducible just because of the way they are written. And actually, I think this can be said for literally everything in this workshop, that once you learn it, it becomes a habit and is no longer a difficult thing to do. Now, science and code, a story of love and hate. Why do I say this? Because you would think that modern computer-based science needs code. So code is a part of science, right? Well, oddly, for whatever godforsaken reason, code is almost never mentioned in the things that communicate science, which are the papers, which is really weird if you think about it, because yeah, it's part of science, but it's never mentioned. How can this be? So this is what you would see in the paper. You would have some equations or some algorithm descriptions whatsoever. This would be the majestic algorithm. And here in circle, I have something that could be wrong. So of course, this algorithm takes effort to derive. It doesn't take effort to share, in the sense that once you put it in the paper, that's all you need to do. It could have a human error in any line. And researchers use other people's equations or other people's algorithms. However, I want to point out that this is just a description of the derivation of this number r. So this thing is always in the paper. It clearly is science, and we do not have to trust that this is true. We can check. We check all the equations that lead to one other. We check the logical connection between the paragraphs. We check all these things. We don't assume them to be true. On the other hand, we have the code. So this is what someone would write to actually produce the papers for this figure. And similarly with the algorithm or the equations, this takes effort to write and even more effort to optimize. It takes little effort to share. Not zero, but little, as I will show you in a moment. As in the other case, human error can be in any line, and researchers use other people's code. Now, the crucial thing here is that this is the thing that actually produces the value of R. Whatever statistical analysis you have done in your paper, this is where it is produced. It is not in the description of the paper, it is when you run the code. However, this is not in the paper, not science, and we don't see the code. We have to trust that the authors wrote the code correctly. Why is this nonsense happening? I do not know, but I'm definitely on a lifelong quest to change this, because it's complete nonsense. So, I stand that the only way for 100% true reproducible science is to share code. I don't think it's possible otherwise. And there are some reasons for that. Firstly, because more often than not, a human language-based description of code is not enough. For example, here we have a nice snippet from some kind of methods section from a Nature paper that describes their actual code. So this is a description of code. And in these red circles, I put things that are ambiguous when it comes to code. They are things that could be interpreted in different ways or could be implemented in different ways. The most trivial way is this span of 25%. Where do you center the span? Do you center it on the median of the distribution, on the mean of the distribution? Does it make a difference? Do you just do the first 25%? All of these things are ambiguous because when it comes to code, everything has to be 100% precise. One more thing that I circle here is that they say that they did their regression with the R statistical software. And I just want to point out that if you say we used Python to do our analysis, and this is where you stop your sentence, this is as useful as saying we used a computer to do our analysis. This is how general this statement is. It is useless. So there are other reasons, though, that the value of some variable may be forgotten in text. I mean, we are humans, we forget things, that's normal. However, I would argue that by definition, code cannot even run unless every variable in code has a value. So if you share your code, it's not even possible for you to forget something because the code wouldn't run. So the conclusion is please always share your code. Even if it isn't good code, it makes a huge difference. Like badly written code that is shared with the paper is so much more useful than no code shared with the paper. I cannot stress this long enough. Now there is one more thing I have to stress here because unfortunately some seniors piggyback on this to claim that it doesn't matter that we make our code reproducible. So to clarify here, I'm focusing on a small aspect of replicating a scientific study, and this aspect is given exactly the same input, produce exactly the same output. So compute exactly the same things in exactly the same way. This is what I call reproducibility, and this is not the same as replicability, which is of course a much more broad thing and a much harder thing because of course you need to describe your methods well, you need to add their caveats and limitations, you need to do a lot of things so someone can replicate your study. So that's a much more general thing. I'm talking about recomputing your study. And what I want to say here is please don't fall into the trap of thinking, oh, I have described my methods enough, so I don't need to share the code. As I said, there are many things that can go wrong, and sharing code can only help. It cannot make things worse. It can only help. So please share your code. Please, if you publish a paper, share your code with it. It really doesn't cost that much. I'm not telling you to make it perfect code. I'm telling you to just share it. Let me repeat, please share your freaking code. It can only do positive things. So now I will start giving some advice which I think help make a scientific project more reproducible. And the first thing is something that I call the principle of least gears. So if your scientific project was to come up with a device that you can use to blow your nose, The clear solution to this would be what happens on the right. It would not be what happens on the left. What I'm trying to say with this figure is try to minimize the different gears that you use in your project. If you can use a single programming language or a single programming environment for literally everything in your pipeline, from submitting jobs to cluster to generating figures, then I would strongly recommend that you do this. For example, one pipeline would be that you use Bash to submit to a cluster, whatever library to plots over the earth, NCView, or however these things are called, and then you use Python to analyze. If you can use Python for all of these 3 steps, you should use Python for all of these 3 steps. And the benefit here is that the reader, or the reader of your paper, has to read a single language and has to only run a single language. Now, the main benefit is on the B part, because it is much more easy to make things work if you just have to run one of the things. Yes, you can submit jobs to a cluster if no one knew this so far. Yes, you don't need to use Bash. You can use Python to submit jobs to cluster. That's very much doable. Another thing that I will advertise is that you can use software that were built to help you have, let's say, project templates, or help with reproducibility, or help with logging your data into a log of when data were produced or with what script. One of these projects is this thing called Dr. Watson. Full disclaimer, I am the lead developer of the thing, so this is of course partly advertisement, but truthfully we made this because we really were kind of fed up with how hard it is to manage a project, and we thought it should be easier. And indeed, if you use some of these tools, it is much easier. So this tool, for example, is just a package for the Julia language that is used within the language itself. So it is not an external tooling service. You just alter your scripts by adding one call to one function, for example. And it can help you with many things that would be useful for managing scientific projects. I will not list them in detail. You can go to the documentation of this thing. What I will do list is that, well, last time we checked, there weren't exact alternatives to Dr. Watson in Python, but there were similar packages in Python or many other languages. Here I'm listing some of these packages. I think the most well-known one is Sumatra, and there is also ReciPy and Cookie Cutter for Python. And if you use MATLAB, there are some others as well. So there are tools out there to make this job easier, and please do consider them. It could be useful. I mean, part of the story of what this workshop wants to convey is that you should think about the tools you're using and consider that maybe using more modern tools will make your job easier. That's one of the messages this workshop wants to convey in the end. So, the other thing that I find, and many people find very, very useful, is to have a habit of having a specific structure or template for your scientific projects. What I'm showing on the right is the template I follow, which is the default of this Dr. Watson thingy, and I use exactly the same template in exactly every single science project I have. Doesn't matter if I am analyzing human behavior when playing music, or if I'm analyzing radiation at the top of the atmosphere. That's exactly the structure I use, and that simply makes me how to say, navigate, is this the correct word? Yeah, it makes me navigate my project faster, and importantly, it allows me to reuse, let's say, management code that I have written, because the structure is the same. What only changes is the functions inside. And as I said, many, let's say, project template providing packages exist in all languages. So please do consider having a specific structure and stick with it and just use it. Okay. Now let me address something that many fall victim of, and this is notebooks, like Jupyter notebooks, or Weave notebooks, or Pluto notebooks. These are a fancy new way to code that makes a mixed medium that interlaces code, markdown, or text, and output of the code, most typically figures. Now this is really, really nice, but you have to be aware. These things are very, very good for presentation purposes, in my opinion, and in most advanced programmers' opinions, they are not good for creating a code base. And there are several reasons for this. Some reasons is that notebooks, with the exception of Pluto, are full of hidden variables. So if you type x equals 3 in this cell of the notebook and then delete the cell, the definition x equals 3 exists within the language. And if you typed then y equals x plus 2, y would actually have the value 5, even though in the actual notebook there is no x defined anywhere. And this is obviously bad for reproducibility. I hope it's obvious why. Notebooks do not communicate well with each other. It's difficult to include notebooks in other notebooks. Notebooks are hard to update. You need to run them through their server to actually run them. So you need to start the Jupyter server to run a Jupyter notebook. And it is very, very hard to version control notebooks exactly because they include all of these things in one document. On the other hand, scripts are cleaner and train you to use the source folder structure, where if you have some functionality that is repeated twice at least, you just make it into a function in the source code. So my suggestion would be to use notebooks for structuring reports or drafts, for plotting scripts, or for presentations, if you want to present code and its output to people. But if you already use a notebook for a week or so, maybe it's time to drop it and go back into an actual editor, like VS Code, for example, and use this for your day-to-day work and establish a code base. Something that some people may have not realized yet is that modern IDEs, integrated development environments, are truly powerful. In VS Code, you can create Jupyter notebooks. You can evaluate code line by line. So if I have here the script, I can evaluate the screen line by line and have the output on the side, just like I would do in Jupyter. So maybe you should start rethinking if you really need Jupyter notebooks for something like that. Yeah, and you can create Jupyter notebooks entirely within VS Code. So that's my advice. So remember, notebooks are just a fancy way of grouping code and plots at the same time. Really, they aren't something more advanced than that at a fundamental level. So they are not as necessary as you might think. Okay, another thing. This is a general tip. Try to make things as simple as possible, but here I try to make it specific in scientific code because sometimes we tend to over-engineer things. My advice would be to avoid creating new data structures or new classes or new whatever, and to use native ones as much as possible. For example, you want a named parameter container, maybe a dictionary is already good enough for you. Use the simplest data structure that does what you need. And always favor existing data structures from existing packages than rolling your own, right? So don't reinvent the wheel. That's a general guideline, because an existing package is already likely something that is already well tested. So you save yourself the time of testing the new thing you have created, because now we learned in this workshop you should test your code. So if you write less code, it's your benefit. You don't have to test it. That's completely different from what I said than of practicing your skills. Remember, in block 3, I recommended you should try to rewrite functions that exist in packages, but this is for practice reasons, right? This is not for your job. This is for becoming better at coding. Separate these things. When you do your job, try to use existing things as much as possible. However, of course, there are reasons to use new structures, data classes, or whatever. For example, sometimes it's necessary for performance reasons, for dispatch reasons, for algorithm deciding arguments, where just using strings is not enough anymore, or namespace establishment, etc. There are reasons. Of course, sometimes there are reasons. But think about it. First, decide if you start creating a new class, decide first if it's actually necessary. All right. So since we're talking about reproducibility, that's one more thing we need to talk about, and this is deterministic code. Now, if you think about it, computers are almost entirely deterministic things, which means you should also have deterministic code. And to understand what this means, let's take just a brief moment to try and comprehend what random number generators are, in case someone doesn't know already. So with the exception of some true entropy sources, random number generators that your computer uses are not actually truly random. For example, some of them are chaotic maps. So they are chaotic dynamical systems that are given by this rule with some function f, some real function that takes a real number and gives you another real number. Now, what happens if you apply this f function many times, you get a sequence of numbers, and the sequence is typically distributed uniformly and sufficiently randomly in the unit interval. So this gives you a sequence of numbers, not random numbers, but numbers that are sufficiently and uniformly distributed in the unit interval. And then what your code or what your library actually does, when you say, for example, when you call this function over here, so this is a function that gives you a random number that is Gaussian distributed or normally distributed. What actually happens in the pipeline is the following. First, the global random number generator is taken or initialized from the state of the language. So if it's not initialized, it's initialized here. So you get this RNG object, which might be the default random number generator. And this random number generator has this x0. This is called the seed. Then there is one step taken with this random number generator. It's like iterating this chaotic dynamical system for one step forwards in time. And then you get this new number, this x1, which is between 0 and 1. And then by using the inverse of the cumulative density function of the normal distribution, you simply convert this x1, which is uniformly distributed in 0, 1, to a number that is distributed in whatever distribution you want. So that's how the process works. And my advice here is, if you use random number generators, you should explicitly set their seeds always. So instead of allowing the language to decide the first random seed, which typically depends on time on day and temperature of CPU and whatever they use, I do not know, use a specific one. And in fact, I would argue it's even more transparent and even better for performance, by the way, if you explicitly use a random number generator. For example, this is how you would do it in Julia. Instead of typing x equals rand, parentheses, so give me a random number, then you would first initialize this random number generator object, and then you would give this object to the rand function. So every time you would call this rand function, if you give it the same object, it would give you exactly the same sequence of numbers. So that's how you would write deterministic code that still has randomness in it. All right. Any questions so far? Because now we're going to change topic a bit, like a lot, maybe. All right. So something that may happen often to you, as it has happened to me in the past, is that your project works and you're so confident and comfortable in your project, and then you share this project with another person and nothing works. And you're like, it worked on my machine, why? So what you want to do is avoid this hellhole that I call it works on my machine. You want to detach your project from your machine as much as possible. How would you do that? Well, the most important part here is that your project must be bundled with a list of versions of every package you have used and their dependencies. Because most of the time what happens is that the other person tries to run your own code, but with completely different package versions, perhaps even language versions, and this sometimes will not work. So how do you do this? There are only language-specific solutions. We will show you in the next slide how. And yes, when I say here a list of versions of every package you have used, your own code is one of these packages, so your own code also has to be versions, yes. And we will discuss this in a moment, how to actually version your code. There is a second reason why things will work only on your computer, and this is that you rely on absolute paths. So you have a path to a file, an NC file or whatever, you load this file to analyze whatever atmospheric thingy, I do not know. But then when you share your scripts, the scripts don't work because this file, even if you shared the file, the absolute path will be different in the machine of some other user. So to avoid this is super simple. You simply don't use absolute paths. You only use relative paths. So you try to give path relative to the root of your project. And that some of the tools I mentioned can automate this for you. For example, Dr. Watson has this function that always returns the path to the source directory. It doesn't matter where you are, where you call this function from, or where the source directory is. It automates this for you. So avoid absolute paths and use package versions. Here's a nice meme for the absolute path. Someone shares this file or shares the path to this file believing it's a URL, but of course it's not a URL, it is a local path to this person's computer, so no one can access this path and actually see the exercises. Okay, so before we show you how to bundle your project with versions, let's first try to understand versions. First of all, a version is a unique and changeable identifier of a code base's contents. It is very useful. It establishes reproducibility, compatibility, and at least tries to eliminate the dependency hell. Any software used in published research must have an associated published version. If not, it is like citing the conversation you had at the bar with that dude. So if you use some software in your research and you say this in your paper, you say we used icon, you have to say exactly which version, and this version has to be published and has to be unchangeable. No one should be able to change this version in any way in the future. So this is exactly how citations work, by the way. When you cite something, it's a reference to something that exists. No one can change it. It's there. Same thing with versions. Now, the versioning system is called semantic versioning 2.0, and it is a well-established standard for versioning software. The TLDR is that, given a version number that has this structure, the major.minor.patch, increment the major version when you make backwards incompatible changes in your code base. Increment the minor version when you add new features to your software, but in a backwards compatible manner, which means whatever functionality existed before remains unaltered. And increment the patch version when you simply make backwards compatible bug fixes. For example, a code using version 1.2.1 is compatible with versions 1.2 all the way to 2. 1.2.1 all the way to 2. A code using version 1.4.2 is not compatible with version 1.3 of the software because this code may potentially use a new function that didn't exist in version 1.3. I hope this system is clear. If it's not clear, you will really, it's really easy, I promise you. So you really will get the hang of it the more you see versions. And furthermore, I stand that all software should have a changelog file with noteworthy changes. Whenever you publish a new release that has noteworthy changes, these changes should be written in human language in this file. This is my opinion. Okay, so one project should be one environment. Most programming languages allow the concept of environments. This is exactly how you bundle your scientific project with a list of package versions. So an environment is, you can think of it as a self-contained space where one can add packages to the space and track package versions and specify compatibility bounds to packages without affecting any other space or any other project. So once you activate this space, which is called environment, the packages that you load when you use import statements are the versions specified in exactly this environment. They are not the global versions, they are not what you installed in your other project 5 years ago, they are what is for this project. This, and the good thing about these environments, of course, is that they are shareable. You can give them to another friend of yours, or not friend, doesn't matter, and this other person can instantiate the same environment, and this will make their computer have exactly the same version of packages as your computer when you use this environment. And this allows for reproducible code by ensuring that everyone runs the same versions. So by default, there is this global environment, which is always activated when the language starts, unless you say otherwise. And that's why I say each project should have its own environment. And whenever you work on the specific project, the very first thing you should do is just activate this environment, nothing else. So to create or activate an environment and then add packages to this environment, that's how it's done in Julia or in Python. Julia also has a named version that I don't mention here. Here you activate by path, here you activate by the name of the environment. Pretty much the same story. It's really easy. So this really isn't a lot of work to have unique environment for each project. Okay, so now let's see how we would bundle our project. So how we would actually specify versions to this environment. So what happens is in either Julia or Python, your package manager tracks a specific file. And in fact, this file is the file that defines the project or defines the environment. And it looks like this in either Julia or Python. And you see this line has a specified, this file has a specified location or command that allows you to give specific versions. For example, here in the Julia version, I say Dr. Watson is version this. And by default, this means that this is compatible with the semver syntax. So this means every version from 2.9 all the way to 3. The same thing happens in Python. What else is there? Well, okay. The rest is information of how you would get versions of the dependencies of your dependencies, because of course I include here this Dr. Watson package, but the package by itself depends on other packages. And of course maybe you want to know the version of these packages as well, right? So you can also access this information. Okay, and then the rest is how to create this environment. So now I will describe, yes. So this is generated automatically when you create an environment. What you have to type, in my knowledge, both in Python and Julia, is the compatibility versions. This is something you have to do yourself, correct? You have to do this yourself in Python as well, right? Yeah. So the initial version of the file, so to say, is auto-generated, but then you specify the versions. Yeah. Okay. So there are commands to make it even easier. Cool. All right, so here how I go about to making a reproducible project that I publish, a reproducible code base for a project that I publish with my paper. I started Dr. Watson project, which is this default template I told you, and I add into this environment whatever packages I foresee using. Then I open my VS Code, and I have 3 columns in my VS Code. One I call script, the other I call the source, and I also have a console open if I want to play around with some commands or access the documentation strings or whatever. Then I start doing my analysis in the middle column, which is the script, right? So there things are very sloppy. I'm sloppy there. But as I progress and I write my scripts and I finalize my work, then all the functionality that is of general purpose goes into the source file. And remember, things that are in the source file can be documented and can be tested. Of course, periodically I reorganize the code base if I need into more files, more scripts, and more source files, and more tests or whatever. And then after my project is done and I have produced all my figures and everything and I'm ready to publish. So what do I do at this point? I make one script per paper figure or per paper table that needs numbers. So one script produces figure 1, one script produces figure 2, whatever. Then I publish the entire code base, the entire code repository. This includes the README file. This includes the project.toml file that defines the dependencies of the project. And this includes the manifest file, which is the Julia version of all the dependencies of all the dependencies and the exact git commit that the dependencies are used at. Then I go to zenodo.org and I assign a digital object identifier to my GitHub repository. And then I use this digital object identifier to cite my code base in my paper as if it was just another paper I cite. No difference. And I will show you the example for this code base, which I have to find first. Yeah, give me a second. I should have prepared this. I forgot. Yes, perfect. So this is how it looks like over here. All the files I described are here. These are my scripts over here. They do some analysis, and I have another folder papers. These are, as you might imagine, the scripts that produce the 5 figures of my paper. And this is the source directory. It has, I don't know, some definition of how to compute cloud albedo or whatever, things that are useful to me, for example, or to my scripts. And then if I go to Zenodo, I would have to log in now, so I won't do this. But anyway, if you go to Zenodo, what happens is you can link your GitHub account with your Zenodo account. And then there is an option over here. It's really easy to find, I promise. But you go through this option and you go to so Zenodo lists your own repositories, okay? And you go to this repository you want to publish and you click a very simple button that says turn on DOI, turn on the digital object identifier. So you turn on the digital object identifier for your repository, which is this code repository over here. And then the only thing you have to do, really simple, you go to these releases. These releases are, let's say, how do you call this? This is exactly like tags, but integrated within the GitHub system. So you simply assign a name to the state of the code at this point in time. So you just create a new release over here. You put whatever name you want. If you want to put a tag, you also put a tag for Git. And then you click release. Somewhere over here, there's a button, publish release. And what happens at Zenodo now automatically, Zenodo stores this release in their archive and creates for you a BibTeX entry that you can copy into your LaTeX paper and just cite it. It really is as simple as that. So that's how I go about to do these things. Yo, this is George from the future again. I just wanted to make explicit this integration with Zenodo because it is really straightforward. I just wasn't logged into my account. So now I'm logged into my account, and the very simple thing I have to do is just click the drop down, go into GitHub. This will already have listed for me the repositories that I have enabled. And you see there is this simple toggle over here that I can click this and make this on. And there is this repository over here that I can click. And now because I have already created a release, you see there is automatically a DOI. a digital object identifier. I can click on this digital object identifier. Now this is a forever archived version of my code base. No one can alter it in any way. And I just want to highlight this is not even published, yet it already has a lot of views. So this reiterates what I said much earlier in the workshop. People want to see your code. This is code for a paper that's not yet published, yet people have already seen it. So just to make it obvious that people definitely will want to look at your code if you do share the code. And lastly, you have the DOI over here. I cannot make it possibly more obvious. That is the DOI that you can turn into a BibTeX entry or whatever you want. All right. So the gist now is that the first thing you have to do is bundle your project with the appropriate environment. So create an environment for your project. All the packages you use there, obviously add them to their environment. The other thing you have to learn, if you use Julia, it's already in the project template that you have. If you use Python, you have to learn how to do it, but I assume it would be trivial. You have to be sure that you activate this project before you run your actual code, okay? That's the whole point of having an environment, that you activate it first. What's up? George from the future again. So I really wanted to quickly showcase this small thing that I said, that you have to be sure that you activate your environment before running your projects, and actually to honestly just highlight why using a software like Dr. Watson makes this process so seamless. So I have open in front of me the default project template that we provide for the Julia language, and this template shows you how you do this, how you activate your project by default before running it. And you do this by using Dr. Watson, specifically this very nice macro from Dr. Watson called @quick_activate. So whenever I run my script, so imagine that the thing on the right is my script. It is located in my script folders, as you can see. And there is a file on the left that is something from my source folder. So this is something that comes from my source, and it is actually useful. So the way it works is every script uses Dr. Watson, and then it calls this quick activate macro. And what this will do is automatically for me ensure that it activates the project that this file is located into. And then afterwards I have this source dir function, that this function simply will always find the source directory. And now I give the output of this function, which is the source directory, to the include function, which includes the file. Now I brought the function dummy project function into scope, and that's honestly how I do it. This is how every single one of my scripts starts, and it simply makes me not have to worry about whether I'm on the correct project or whether my collaborator will be on the correct project. This absolutely and always ensures that both me and anyone else that will use this code base will be on the correct project. Yeah, that's it. Thank you. And then you have to collaborate with your exercise partner and ask them to reproduce one of the papers of your, one of the plots of your paper. So your partner has to fork your repository. Well, they already have it forked if you manage to do the collaboration exercise on GitHub. If they don't, just fork it now. Their goal is to fork your repository and try to reproduce one of your paper plots. That's the ultimate goal. If you can do this, you have completely succeeded in making a reproducible project, and you will be super duper proud of yourself. And after you are able to do this, then it comes the amazing thing that you can actually cite your code base. Like, imagine how amazing this is. After 5 decades of papers not sharing code, you will be the change. Like, this is mind-blowing stuff. And it's really easy. You just go to Zenodo, link your GitHub account. And once it's linked, go back to GitHub and click, do this thing that we call a release. Really simple. Just write a small summary of the release, click publish, and then Zenodo gives you the BibTeX entry that you can immediately add into your paper. If you don't want the BibTeX entry, you can also get the direct digital object identifier link. That's once again a permanent link, and then you can transform it to BibTeX later using this website I have here. And then you have really succeeded in this life. You have a fully reproducible code base. You cite this code base in your paper. Everyone that reads your paper can immediately reproduce your work and continue it without spending months trying to figure out how you did things. So that's it. That's the end. I have one slide here with further reading materials that you may want to consider at some point. In the future, let's say, if you want to revisit the things or you want to learn even more, all of these resources are really, really nice. And I want to close with this nice meme that I love. So I really like this website called Programmer Humor. And here it says, does he bite? No, but he can hurt you in other ways. Understanding programming means doesn't make you a dev. So while it's true that the only thing that can make you a dev is really hard work, it's nice to have, let's say, a fun outlook. And I really hope that with these newfound powers you got from this workshop, you will really have a better future. And I appreciate code more. Thanks a lot for attending.